Hi,
Yes, I
yes.
hear you. I am.
Hello. I'm 3 minutes early.
thank you again. It's a wonderful place to be here, and thanks, Freddie, to make such a wonderful arrangement. I'm really looking forward to the coming days, particularly the dinner. I think it's a really nice place for the dinner at this tower. I'm Shu Tingyang. I'm working at the Danish Meteorological Institute. I'm the coordinator of the TipESM project. The project is, as you see from the title, it's exploring the tipping points and their impacts using Earth system models. And we are now about a little bit more than a year into the project. And so we have already got many exciting results and simulations. And I will try to use not much time because I think we have a very exciting program in the coming 2 days, and also in the following days where we have our own back-to-back project meetings. And so you will hear much more on the things I will present here, and in more details. This one, yes. So for those who are not familiar with the project TipESM, we have as you see from the title, the project objectives, or the overarching objective is to deliver a step change in our understanding of the climate tipping points in the Earth system. And of course, together using the Earth system model, we will do a series of research, including understanding the impacts of the tipping points to the ecosystems and society, and combine with to understand, try to deliver the early warning indicators and safe emission pathways that can minimize the impact of the tipping points. So the key is the Earth system model. The key tool in our project is the Earth system model. Why Earth system model? I think that you don't need me to do a lot of introduction, but as you know, Earth system model can represent explicitly the physics and biophysics of the tipping processes. And it can include the physics and the interaction, the feedbacks between different tipping points. So it allows us to do not only see what happened, but also to understand the mechanism and the physics behind it. And as an example, here it's an example of the Earth system model, UKESM, where you can see the model include, besides the normal AOGCM, where the atmosphere, ocean, sea ice couple together, it also includes the atmosphere chemistry and aerosols, the marine biogeochemistry, and also the land physics and the dynamical vegetation included in the model system. So we are able to say, simulate explicitly. In addition, I forgot to mention that in this UKESM, it also have an interactive dynamic ice sheet model that's representing the ice sheet of Greenland and the Antarctica. So as you see here, the model can simulate the dynamic interaction of Greenland ice sheet and Antarctica is not shown here, but the dynamic and the leading to the change of Greenland ice sheet due to climate change, and also the feedback of the ice sheet processes back into the climate system, in particular the ocean circulation like AMOC. And as you see here on the left, the model can have a rather realistic representation of the missing layer depths in the North Atlantic subpolar gyre regions. And it also simulates the missed layer depths collapse in the future. So it actually can represent or simulate the tipping phenomena. And in the project, in the past year, we have an extensive collaboration together with the TipMIP, the tipping point modeling intercomparison project, and the many of the Earth system model groups internationally, and to discuss, to build the experiment protocol for Earth system models that can force us to investigation of the tipping points and the tipping point interactions. And the experiment protocol, we decided that should be an emission-driven, run in an emission-driven mode, start from the pre-industrial control, where as our reference, and then start from branch from the pre-industrial, we have a ramp-up simulation to force the climate have an warming, keep in a global warming rate at about 2 degrees per century, and then at some levels of the global warming, and we stabilize the simulation by putting setting a zero emission in the model, and so we can use those simulations to investigate the likelihood of the tipping dynamics and how they interact and the impact. And then to investigate the reversibility of those phenomena, we also run and ramp down simulation. And so to look at if we have the system able to go to the forcing are reduced and how the tipping phenomena will change or not. And currently, there are already 13 Earth system modeling group had committed to perform those experiments. Among those, 6 of the European groups that joining the project TipESM had already performed, have finished, complete those experiments, or are ongoing of making those simulations. And there also the CESM American group also had performed those experiments. The Japanese MIROC modeling group also had performed the simulation, and as well as the Australian modeling group assess. As example, here shows the surface air temperature response to those protocol, and also some of the models we actually also try to see at the more than the tier 1 ESM simulation protocol, that we have more warming levels in the simulation. And the protocol is based on the assumption that the response is calculated based on the transient climate response to the CO2 emission, accumulated the CO2 emissions, and also at the zero emission rates, that would lead to a warming stabilization. And as you see here, most of the model, the simulation seems to be able to hold this assumption. And even though, particularly at the low warming rate, low warming levels. And for some models, when the global warming levels are strong or high, they seems to, the warming seems to continue. And that's actually indicating the feedback mechanism between the climate and the carbon cycle. And to check the AMOC, how the AMOC will respond in these simulations, as you see here, we've given some example of different models in the project. As you see, during the ramp-up run, the AMOC will decline constantly, but it seems no abrupt change or abrupt collapse will happen, even though the AMOC strength will continue to decline. And at the zero emission, however, the response seems to be different from model to model and from different global warming levels. And as you see here, at the lower global warming levels, some models have a recovery of the AMOC, and some seems to stabilize the AMOC at the relatively low level. And but on the very high global warming levels, these AMOC will continue to decline, even though probably at some sort of a less strong as the ramp-down run. And then on the recovery simulation, when we have the rundown simulation, the AMOC seems to recover and recover faster than the rundown. As you have here, some of the model had a dynamical ice sheet model included. I don't think I have time to talk any details, but you will hear after the break, where from 2 presentations where it will present some early results on how to identify, if we identify any tippings in the ice sheet and how they change, and also this kind of simulation will enable us to continue the study on investigating how the interaction of the ice sheet melt and the ocean, particularly the AMOC simulation. And one of the goals of this project is, of course, not just making simulations, but to understand what the tipping point. Can we identify any tipping points in both the physical system and also the biogeochemistry system? As you see here, in the project, we have developed an automatic cataloging method to apply this method on the simulations and try to identify in the physical space if are there any tipping points. And as you can see, there are actually, in the current Simi6 example, we could identify both the abrupt change indicating by the small letters and those dots, big circles, and also complete the state change of the phenomena, and like the sea ice, where the largest red circle, where you see the sea ice will be completely gone in the future, and also you see like AMOC, there are also some the change of states that are identified. And currently, this method has been also tested and adjusted to the ocean biogeochemistry variables, and particularly you see here for the net primary productions, where the sort of abrupt change are also identified in some of the model simulations. We also tested the early warning indicators for the Earth system model simulations. Here is just a very early test results where we applied the classical early warning indicator method based on the critical slowdown theory, and check if the model are able to simulate abrupt change like sea surface salinity in the North Polar drier region, and see, as you see here, we are able to identify some of the features that indeed there are critical collapse of the polar gyre, but the method seems to be sensitive to the choice of like the amplitude of change and the duration where we calculate those indices, and the more research will need to be carried out during the project, and particularly we will apply this research on the simulations we made in the project. And the project also have a large element on identifying climate-driven tipping points in the ecosystem and the society. In the project, there are many, here we listed 9 subsystems that could be tipped in the future, and group it into 3 big realms of territory ecosystem, marine ecosystem, and the societal system. And we applied both the data from our simulations and developed either the Earth system model or special ecosystem models to understand how those elements are changed. And here is an example, a model and a process-based model for great ape population dynamics are developed, and that are driven by climate information and encoding in many different processes, and combined with the data had already published, and to understand how the ape population will be changed, and if it could tip in the future. And another area is to assess the impact of the tipping points. And as you see, and there are some early results now already showing that when the subpolar gyre will collapse, and it seems that there are some area in Europe might increase of the heat, warmest days and the heat wave in connection with the tipping of subpolar gyres. And to summarize, as we said, we have developed the protocol, and the simulation are already ongoing for the study of investigation of the tipping points in the Earth system. The data will be available soon on the ESGF data nodes. And there are many research going on at the moment to study both how to identify the tipping, if we could predict the tipping, and also how the tipping elements are interact with each other. But we do not only the, so to say, the TIP-MIP simulation, or in the project it is the TipESM core simulation. There are also some other simulations we think we need to carry out to be able to fully understand the tipping phenomena. And one is the tip core experiment, tip force experiment, we call it, that so to say, to make it happen, if we don't see a tipping, and can we make it happen to make the tipping happen in the Earth system? And the protocol had already been discussed, and the simulation will start soon. And there are two other simulations that the project will carry out. One is the TipESM ensemble simulation, where we will, if we find any tipping phenomena in the above two simulations, we will then try to understand, to identify the generate an ensemble of events, and to study the downstream consequence of the impacts, and also the tip domain experiment, where we use the offline models to understand the robustness of the tipping points. I will stop here, and I'm sure there will be many more results you will hear in the coming days, and we are really looking forward to simulations. Thank you.
For Niklas online.
Niklas is online, yeah. I can see him.
Yes, I'm here.
Okay, hi Niklas.
Sebastian, do you hear me though? Sebastian, I slightly modified the slides on the Google Drive. Is it a problem for you to get them updated, or do you prefer working with the offline ones that you show now?
I'm looking at the faces of my companions.
How many updates do you have? Because I've done this.
Maybe we do without the updates. That's fine.
Yes.
Okay.
Thanks.
Or maybe I have a different idea, because I could probably just steal the screen, right?
Yeah, let's try.
So on Zoom, I'm sharing, but...
Yeah, now we see you as well.
We do not see your slides. Is it this? Is that what it is?
Yeah, I think that could be it, yes. We see.
You see the slide moving? Yes, perfect. I see it, almost see it. All right. I think then
okay.
I just stop sharing once you take over, Sebastian.
Yeah.
So, first of all, my sincere apologies, everyone, that I can't be there in person due to family and health reasons. It was just impossible. I'm very sorry. I would have loved to come. And yeah, I hope you guys are gonna have a great week, and I'm of course jealous that I can't be with you, but I think that from the ClimTIP side, still with Sebastian and Kurt and everybody else there, everything will be in extremely good hands. I just give the intro and then hand over to Sebastian to sort of not destroy this sort of really in-person feeling that you guys are having. So yeah, what is ClimTIP? Climate tipping points, the main overall title, uncertainty-aware quantification of climate tipping potential and climatic, ecological, and socio-economic impacts. It's designed to be complementary to TipESM, as Shooting just introduced it. And yeah, we have 1 year of experience of working very nicely together and having very nice synergies. And I'm very much looking forward to continue that. We're 24 partners from 13 different countries across 3 continents, including China, so the Asian continent, and the US, the World Bank, and just in a few bullet points. So we started in March 24, so a bit more than a year ago, and will then run for 4 years. And so let's say 4 main aims that we have is to improve the mathematics, the underlying theory of tipping elements, and there is a presentation in ESMs. To constrain as far as possible, and it's tough, the position of critical forcing thresholds, to identify safe operating spaces, or to see to what extent that is actually possible, or maybe the uncertainties are so large that it is not. But that's of course also important information. Then we want to do high resolution simulations of impacts of major tipping events and see how it really investigate the consequences on other climate subsystems, but also very strongly focusing on ecosystems and biodiversity and society and economy, and in the later work packages. And with all this, the aim is that we provide useful knowledge for ongoing IPCC reporting processes. And those are the 4 major tipping elements that we decided to work on: the Greenland ice sheet, the Atlantic metal overturning circulation, the Amazon rainforest, and the West Antarctic ice sheet, both to the extent possible from an observational side, but also from a modeling side. And with that, I would hand over to you, Sebastian, and these are exactly your slides, so you could also just go through them like
Yes, I was going to suggest that. Thank you very much.
Yes.
Yeah, so welcome and thanks for the invitation to the great place here and all the support. And because we all work on the same, more or less the same aims in related projects, I think it's really great to have this joint conference and not stay separated in individual projects. I think that makes a lot of sense. And on the remaining slides, I just point out what are slight differences of focus in ClimTIP for those who work in TipESM who might not know, and show 2 or 3 glimpses into results, and then let's let science speak for itself in the remaining days. So one slight difference is one of our work streams. So several work packages are always in one work stream. We have 5 work streams. And a difference is we have some focus on fundamental mathematical theory, also involving machine learning in work stream 1, where we really work with more or less conceptual models. And this is one example about rate-induced tipping, where you can have some, maybe I can use the mouse here. Yes. And so on the top, you see some ensemble members make a transition away, and some other ensemble members, wow, we have 2 mouses, perfect. And the blue ones, the large blue mouse, are the ensemble members who don't tip. And in the classical early warnings, that would be like autocorrelation variants, they are not really made for this situation. They cannot distinguish these cases. That's not what they're made for. But with a machine learning method, sometime before this separation, one can predict it. So that's one of the recent results. And Niklas, if you go to the next slide. Thanks. So that's workstream 2. I'm very excited to see from TipESM the simulation results, we are also doing related simulations. It will be interesting to compare. So yeah, we focus on these 4 systems, and especially regarding AMOC and Amazon rainforest. We want to study impacts and how they could tip in complex models now. What we don't do is kind of see what happens experiments. So we always intend to impose the tipping and then see, in case they might happen, what are the repercussions in the climate system. So these are similar simulations as shooting. I mean, it's not a coincidence. We coordinated somehow the protocol. But the difference here is we have concentration-driven models, but they mimic the same situation. And then we go to warming of 2 degrees. And then here we have several cases. So one without tipping, and then you can impose, for example, Amazon rainforest removal, and then see what happens in that case. Yeah, so that's going on at the moment. And next slide, please. Then workstream 3, what we want to do is we will downscale these simulations. There will be statistical downscaling for the entire globe to ERA 5 resolution. So we will have higher than usual resolution of tipping point impacts, and we can run impact studies on that. And there will also be dynamical downscaling that's already running in some selected regions around the globe. Next slide, please.
Maybe let me just say
Yes.
one thing. So the statistical downscaling we do with generative machine learning, and the method that we're going to use for that has been invented by Philip Hess, and the paper about it has just been published, I think, beginning of last week. So I think that's also for if in TipESM, if there is interest in global scale downscaling, we would be very happy to collaborate with these kind of modern methods.
Yeah. Nice. So these are methods that can take several variables into account, that they are also consistent, for example. So that's very exciting. Workstream.
Maybe one last thing,
Yes.
what is also maybe very interesting for TipESM is they do not depend on the Earth system model or climate model that you use for input. So basically, we have trained on observational data, and you could, in principle, just plug in any Earth system model simulation that you have, and it would work out of the box.
Yes, agreed. Yeah. So then, using this data, we'll do some impact assessments similar to TipESM, for example, with vegetation models, where you can force it by the climate response to the imposed tipping, and then see what that means for crop yields, for example, in some regions, or also economic conditions, for example. And workstream 5 is apart from the management. So the next slide. Apart from the management, some outreach activities. We recently had a workshop with climate activists who also talk about similar questions that we'll have tomorrow. So what's the role of what do people expect from climate sciences, and how should we communicate, for example? We might also do that again for a different part of the political spectrum and see what happens there. It was very insightful. So this was in German because it happened in Munich, but we might do other things elsewhere. We are preparing a podcast, so we are always also looking for input and interview partners, for example. We're preparing some teaching material. So yeah, do I have a next slide? I think I have a final slide. No. Okay. I had one, I think. Did you hide it, Niklas? Yes, thank you. So the breakout sessions we'll have in the joint conference, they are ordered by tipping elements, but so it would be good, we already identified some common themes. It would be good to, if you have this in mind, simulation protocols, I think, are more or less finished, but data sharing, can we use each other's data? That would make a lot of sense, I think. How can we join in some outreach and communication activities, and of course in future scientific ideas. And just a few final remarks just for the ClimTIP members here. Our GA breakout sessions on Wednesday afternoon, it's kind of grassroots, so enter your ideas in the tab in the spreadsheet, and then we see how we break up. And the second one is, there will be a separate list or in the ClimTIP GA where you sign that you are there and that you agree with photos used only in the ClimTIP GA, so that's a separate thing that will be coming. And if you have organized, again for ClimTIP GA, if you have organized the workstream sessions already, that's fine, but be aware you can, or maybe it makes sense to upload all the slides also on our ClimTIP Google Drive for our GA, then we can, in the other room, also share from there. That's it. Thanks very much. Niklas, last words?
Have a great conference.
Okay, thanks.
Okay, I think, can you hear me? I think we need to reconvene, okay? So, good afternoon, my name is Marisa Montoya, and together with Robin, I'm chairing this session, which is the first theme, the cryosphere. So we're going to have a keynote talk, and then we will have a short break, and then 3 short talks. So our first talk is by Robin Smith from the University of Reading, and the title is The Reversibility of Ice Sheet and Sea Level Responses at Different Global Warming Levels in a State-of-the-Art Earth System Model. Thank you.
Cool. All right, so thank you, everyone. Thank you for coming. Nice to see you. Nice to be in the opening science act, I guess, for this. So this is shooting already introduced the importance of ice sheets fairly comprehensively, I think. So this is a whole session about ice sheets, and this is a whole talk about some quite detailed ice sheet physics that's really building off this set of experiments that Shooting outlined, the TipESM experiments that we're doing with all these Earth system models. There's a lot of people that work on an Earth system model. I'm sort of the ice sheet guy, so I'm by no means responsible, get the credit or the blame for the whole thing. There's a whole cast of people that have worked on these simulations, and I'm just presenting one aspect of it. Particular mention, though, should go to Caitlin and Tom and Charlotte, who have done a lot of the analysis and made a lot of the plots for this ice sheet talk. So, I was going to hope that I didn't really need to motivate the importance of ice sheets and tipping and ice sheets to this particular audience. There's a lot of things a lot of reasons why ice sheets are important in the Earth system. The one that gets all the headlines maybe is the sea level rise, and obviously that's a big long-term impact. The other big thing that they do, though, is that they're just a massive part of the global freshwater budget. There's a huge amount of freshwater comes off the ice sheets, goes into the oceans. That's a critical part of the ocean circulation. So then we've really got these 2 things that come off the ice sheets. We've got sea level rise as a whole, and then we've got their interactions with the rest of the climate system. And for good or ill, they're also a bit of a poster child generally for the public for climate change, global warming, melting ice. So you can see there's a variety of headlines highlighting some of these aspects. Some of them a little more hysterical than others, maybe. There's a lot of different views on what ice sheets do in the climate system and how they interact with climate change. I'm going to talk about simulations that we've done with the UK Earth system model. Shooting's already introduced some of these graphics, I guess. It's a very comprehensive Earth system model. It's one of the models that was used in CMIP 6. It's also going to be used in CMIP 7. It's got atmospheric chemistry. It's really got a very sophisticated sort of process level explicit representation of a lot of the different parts of the Earth system and how they interact with each other, and that's really important. A lot of the theories, a lot of the knowledge about tipping points comes from fairly simplified models or theoretical views of how different parts of the system interact. And it's really one of the goals of the TipESM project that we take some of these theories and we try and see whether they really play out in reality when you've got a lot of these things interacting in a much more sophisticated way. One of the features of the UK Earth system model is that we've got the interactive ice sheets. This is a pretty unique feature of UKSM, that we've got Greenland and Antarctica. And we've got those coupled in quite a sophisticated way as well. So there's a problem with the spatial resolution mismatch between climate models and ice sheet models. So we've got some online downscaling for the surface mass balance that helps us deal with some of that. We've got floating ice shelves around Antarctica and actual ocean in the cavities underneath those ice shelves. So we've got ocean circulation, we've got explicit melting. We can have those shelves thin, we can have the grounding line retreat. That then very directly feeds back into being able to do our ice sheet physics of grounding line retreat, possible marine ice sheet instability, that kind of thing. Shooting's already showed this one as well. This is really based around these TipESM core experiments. This is what I'm going to be talking about today. that's probably, I don't really need to say anything else about that, I don't think. Shooting said it. So the reason we've got all these results from the UK Earth system model is that we started a bunch of these experiments quite early. And we also did them with a whole load more different global warming levels, not just this 2 degrees and 4 degrees. So we've had a bit of a head start on a lot of this. Shooting's already shown this one as well. So just for general orientation, this is the sort of thing. So this, the one on your left, is the global mean air surface temperature. Blue one is the control. All the different colored lines that rack up more or less parallel to that are stabilization at different global warming levels, or at least they were stabilized. We had this ramp up run, that blue one that just goes, black one that just goes up diagonally. And then when that hits different global warming levels, we stop the emissions and we have a sort of a net zero run that from a climate that was at 1.5 degrees or 2 degrees or 3 degrees or 4 degrees. What you can see there is that for the lower global warming levels, that net zero portion does pretty much stabilize and the global air surface temperatures stay pretty constant. And then as you get up to the higher global warming levels, 4, 5, 6 degrees, you can say even though we've got a net zero sort of carbon thing, we've got warming that continues in those runs. So they're not really stabilized as such. And that's just a feature of the carbon cycle and various other elements of the system interacting as we run those simulations on. This plot on the right here I thought was worth showing since we're talking about the ice sheets. Ice sheets do not see the global mean climate fairly obviously. There's Arctic amplification. But even sort of more nuanced than that, you can see looking at Greenland or bits of Antarctica, they don't see even like the zonal mean climate that you might have. So you might think you've got an Arctic amplification effect of 5 or 6 degrees. That doesn't mean that's what the surface of Greenland is seeing. So it's really important that we do actually run these simulations in a model that's sophisticated enough to resolve regional climate differences. That one. Okay, so ice sheets. I'm not going to talk about Greenland, actually. I'm only going to talk about Antarctica in this talk. Jorge, coming up a bit later, will talk about Greenland. So the reason we care about tipping in Antarctica is really about the ocean and the ice shelves. Sea level rise comes from grounded ice flying off the continent into the ocean, but they're held back by the ice shelves around Antarctica. So if we have ocean melting of ice shelves, that thins the ice shelves, that reduces their back stress, their buttressing effect on the grounded ice. We get more dynamic flow of the ice into the ocean. So we've got these two things going on. We've got a freshwater flux that affects the ocean circulation. That's coming from the melting of the shelves and the loss of grounded ice. And we've got the sea level effect that's just coming from the grounded ice. So this is a little bit of a history lesson. If we zoom in here on the Ross ice shelf, this is some physics that's pretty much already known about. This is probably the most complicated bit of physics I'm going to do in this talk, so hold on for this slide. I'll try and explain it. It should get easier afterwards. So what we're looking at here is a cross-section through the Ross ice, or underneath the Ross ice shelf, moving from, it's not very good, is it? Moving from south to north as you go from left to right along these plots. So time-wise, plots at the top are sort of now, plots at the bottom are end of the 21st century. We've got this cross-section so that the plots are down in depth. That grey bit you can see on the top at the left is a cross-section through the ice shelf. The grey bit along the bottom is the continental shelf. And then the bit without a grey bit on the right of the plots is the open ocean. And you can see, so on the left-hand side is the temperature of the water. On the right-hand side is the salinity. So you can see, if you just concentrate on this top left one, we've really got two water masses here. If you look at the temperature, we've got blue cold water in contact with the ice shelf, and we've got red warm water offshore. So the water in contact with the ice shelf is cold. It's not melting the ice shelf very much. Looking at the salinity plot, it's also quite saline. So this is the densest water sitting on this continental shelf, is cold and salty, and it's denser than the offshore water, which is warm and salty, but because it's denser, it's stopping that warm water from coming up onto the shelf and melting the ice sheet. Skip to the middle line, you can see that the temperature, so this is sort of mid-21st century in the set of projections. You can see the temperature under the ice shelf is still cold, but the big difference is that we've started to make the water under the ice shelf fresher. So this is coming from processes in front of the ice shelf that are making, freshening the water here. They're slowly making the water on the shelf in front of the ice sheet less and less dense. It's still cold, it's not melting, but we're freshening it, and we're breaking down that barrier to the warm water offshore. Eventually, by the time we get down to this bottom line here at the end of the 21st century, we've freshened the water enough in front of the shelf that it's no longer providing a barrier, and we just get all this warm water from off shelf that's been waiting there, flooding under the ice shelf, starting to melt it. That's going to give us a lot more fresh water coming off Antarctica, and it's going to reduce the backstress on the ice sheet. So this set of physical processes has been known about for a while. It's mostly been looked at in regional models for the Weddell Sea and the Filchner-Ronne ice shelf. We've done these projections with UKSM that see it there, and on the Ross ice shelf as well. But that was just one set of projections. What we can do now that we've got this systematic level of runs with simulations at all these different global warming levels is that we can start to narrow down where some of these thresholds are. We can look at it in a much more systematic way. So just for orientation, so the x-axis along here now is the global warming level. If you look at these red runs here, these are different members that are, these ramp-up members where we're constantly emitting carbon, and they're just warming up. So they're moving from left to right along this axis. And you can see, so the y-axis here is the temperature under the shelf. The x-axis is the global warming level. So as we move up through the global warming levels, eventually we get to this threshold where suddenly the temperature of the water underneath the ice shelf jumps up from a cold regime where it's not melting at all to a warm regime where suddenly it's melting really a lot. We see this under the Ross ice shelf at one global warming level and another at a slightly higher global warming level under the Filchner-Ronne. The blue lines here are those recovery runs where we're sequestering carbon and cooling down the climate again. So if you look at one that starts from a warm state up here, you can see as we cool the global climate, we're moving back along this axis, but we don't move down in terms of the temperature of the water under the shelf until we've cooled the global climate much more than that threshold where it jumped up for the warming. So these aren't equilibrium runs. We can't run these out for thousands of years. This isn't a mathematical hysteresis in that sense, but we are running these for hundreds of years for the purposes of human society, human timescales, human policy. This is effectively a sort of, it's reversible, but it's on this sort of hysteresis regime. The gray lines here are possibly more disturbing in another way. So these are stabilization runs, the gray ones. So you can, even though in the transient case, we didn't move to this warm water regime till about 4 degrees, we've got stabilization runs here at 3 degrees and even one at 2 degrees, that if you leave them long enough, they will transition into that regime. So I said this was all being controlled really by that freshening in front of the shelf. So we can look at observations in the real world and we can see that the shelf and the water in front of the Ross ice shelf is freshening. So we're on this trajectory. So what we can do is we can make a plot here of the salinity on the continental shelf against, again, that temperature in the ice shelf cavity. And as we warm up the world, we're freshening in front of the shelf, and we're moving, again, this way along this axis towards fresher waters in front of the shelf. And again, you can see there's really a threshold here in terms of once you've got fresh enough, we suddenly flip up into having warm water under the shelf. So this is all good physics. This is all very interesting. You might even be thinking we could use this as some kind of a metric in the real world for warning when this might be happening. We've got a freshening trend. We can identify some thresholds. Have we got an early warning system here? I would say potentially, but then you've got to take that with a big pinch of salt. This is a climate model with known biases. We have biases in our climate sensitivity. We particularly have biases in the salinity of the water in some of these regional parts of the Antarctic shelf seas. So can you see the caption on the bottom here? global warming corrected. What we can attempt to do is make allowances for those biases. We can map between a freshening rate and, say, the fact that we started from a state that was already too fresh, and we can try and predict where some of these thresholds are, but it starts getting very complicated to sort of transition knowledge like this into a real-world sort of operationally useful system. So that's the ocean under the shelves. We can see there's a fairly sudden transition to a warming regime that's sort of reversible. Looking at the ice sheet itself, we can split that into two parts. So first we can just consider these floating shelves themselves. This on the left here is a plot of the melt from under those shelves, but now taken as Antarctica as a whole. So we're integrating over all the shelves around Antarctica. And if you squint, you can sort of convince yourself we've got about 3 levels here. We've got this low melt state at the beginning, where the PI control and some of the lower global warming simulations sit. We've got a middle one here. This is where the Ross has flipped and started to melt the shelf, but the Filchner-Ronny hasn't yet. And then these warmer ones here down the bottom, which is where we're melting the Filchner-Ronny as well. So our integrated Antarctic shelf melt is very high indeed. This orange line, I don't know if the colors come out well enough on this screen, is an interesting one actually. So this orange line is the 4K simulation that branches off here. So this is where the Ross has flipped already, but the Filchner-Ronny hasn't yet. As that 4K stabilization simulation continues, after 100 years or so, the Filchner-Ronny does then flip. On the other hand, the dotted line that comes from there is where we ramp down and cool again after 50 years. So we've got a simulation there that if we take action fast enough, after one of these tipping points, we do manage to avoid the other one. That's all ocean, that's all basal melting. Surface mass balance on Antarctica at the moment isn't really a big story. It's pretty cold, it's too cold to melt there even in the summer. As you get into warmer futures, that does start to become an important part of the simulation for 2 different reasons. So on the shelf, you can see as we warm up, we start to melt more. We get a more negative surface mass balance. So we're melting the shelf from the bottom, we're melting it from the top. Both of those things are going to reduce the stress, and the melting from the top means we're going to get potentially into a regime where we've got ponding. That could lead to hydrofracture and just the mechanical breaking of these shelves. That's not a process we have in UKSM, but we're working on it. But it's leading on to more physics, more stuff that you've got to consider in terms of whether we're going to cross thresholds or hit sort of catastrophic problems with these shelves. Away from the shelves, looking at the grounded ice, and this is the ice that matters for sea level. We've got the sort of the discharge of solid ice off the ground into the shelves or into the ocean here on the left. Again, if you squint, you can convince yourself that there's sort of 3 different levels. We've got one at the bottom that's sort of control. We've got a middle one with a little bit more discharge in the middle there. That's where the Ross shelf has started to thin and reduce the backstress. And that's very directly linked to a speed up of ice from that sector. And this higher one up here where the Filchner-Ronny has also started to melt, and we have more of a speed up and a large amount of ice coming from there. There's also a surface mass balance part of this question here. And you can see this is now in the opposite sense to what we saw for the shelves. So as the climate gets warmer, our surface mass balance gets more and more positive. So we're snowing more. It's getting warm enough to snow, to have more precipitation from the atmosphere, but not so much that, at least on this higher ground, that we're melting enough. So there's 2 very different things going on. You can see that on a map here. So this is just the total thickness change on Antarctica towards the end of the ramp-up run. So 7 degrees warming. It's a very warm world. And you can see we've really got a split here between the low-lying areas around the side, where we've got hundreds of meters of loss, particularly on these floating shelves. So this one down here is the Ross. Up here is the Filchner-Ronny. This in here is this Amundsen West Antarctic sector where Pine Island is, where we know there's a lot of retreat going on at the moment. But we've also got blue areas where we're building up actually quite a lot of snow. So it's not just a question of mass loss. We've got a bunch of competing processes we have to worry about if we're going to predict what's happening with the mass balance of Antarctica on these timescales. It's a little difficult to see. There's a grey line. There's a grey line, which is the outline of the original grounding line here in the Ross, and a black line, hundreds of kilometers inland. That's where the grounding line is retreated back in our model. So that is starting to... no, all right, next one. Next one's better for that. So this now is looking at sort of the commitment to dynamic loss from Antarctica in these. So we've changed the color scale again. We've put all of our simulations together. The gray lines are ones where the ice shelves haven't tipped into this warm regime at all. Red lines are ones where we have tipped one or other of the ice shelves. And blue lines are ones where we're not only cooling the world, but the water under those ice shelves has got cool enough to flip back into a cold water regime and stop some of that ocean melting. What you can see here is that, and then this is the y-axis is just the contribution to sea level we're getting from the flow of ice from these catchments. So basically you can see as soon as we tip, we start getting significant amounts of contribution to sea level from that dynamic ice, but that just continues. It doesn't really matter whether the water underneath the shelf starts cooling again to recovery. Once we've started that dynamic loss, it just keeps going. And again, we're not talking about 1,000-year timescales here. We're not looking at the equilibrium response. But from the point of view of human societies, 400, 500 years is long enough really to be worried about, and really to call this an effectively irreversible change to the ice sheet dynamics. Just to reinforce that then, so this is looking at the ice sheet contribution to sea level rise in UKSM from these simulations. This is now both ice sheets together. The dynamics of what's going on in Greenland are actually a bit easier to understand, but I won't go there. But again, this is one of those ones where we've got global surface temperature on the x-axis, so the warming run is moving from left to right. As the stabilization runs are then more or less at a constant global warming temperature, and the cooling down runs are the dotted lines where we're moving back along the axis. So the red line, fair enough, we're warming up, contribution to sea level from the ice sheets is going up. All of these stabilization runs, notably also the PI control, have these vertical lines that indicate that sea level is going up regardless of what's happening with our forcing of global warming, although it goes up faster in a warmer climate. And then the dotted lines are moving back left to right, but they're also moving up. So reducing global temperatures, those worlds still have continuing sea level rise at some rate or another. So the fact that we've got a zero, we've got some sea level commitment at our zero global warming level here is important. So that comes very directly from our ice sheet initialization. We initialize the ice sheet so that it looks like the modern day ice sheet, and that includes this retreat in the Pine Island sector that I was talking about. So we have some of this committed sort of sea level rise in our simulation. We can call that a realistic thing. We can call that an unrealistic thing, depending on how we look at it. But it really highlights the importance of that initialization. Again, if we want to use this sort of thing as a system for making predictions about sea level in the real world. Yes, we've got a lot of the physics, we've got a lot of the interactions, but there are very important features of how we set these simulations up that materially affect what level of sea level rise we would predict out of them for any given climate. So, moving on to my conclusions then, on centennial timescales for our protocol in UKSM. So we do definitely have some threshold tipping of the water underneath the ice shelves on Antarctica at around 3 degrees. This is a reversible feature with some hysteresis, I would say. We trigger retreat of the ice sheet that, at least on human timescales, is not something we can stop once it's started. Okay. It's important to remember that freshwater fluxes from the ice sheets are not just a question of sea level rise. They also play a role in ocean circulation and potentially triggering other tipping elements, which I haven't talked about here. And the other thing I think it's really important to point out, I haven't talked about Greenland. Greenland doesn't seem to show any particular tipping behavior on these timescales in UKSM, but it is actually the biggest contribution to those sea level curves that I just showed. So tipping is all very exciting and stuff, but actually a very large but boring signal is probably more of a problem in some ways. I think it's worth highlighting that surface mass balance starts becoming an important part of the question once we get onto warmer worlds and longer timescales. And that's just another reason why we do need comprehensive Earth system models to be looking at some of these questions so we can look at the physics of how all this stuff interacts. But this isn't a one-size-fits-all solution. Issues with model biases and initialization mean it's a little difficult to use this sort of thing as a predictive system. I'm finished.
So thank you very much. I think we decided we would give the floor before to the people online, right, for questions, right? So I don't know if I can I have you have them? Okay. Yeah, it went away.
Okay, so there's a question from Anastasia Romano. How many ensemble members have they done?
So we have 4 of the ramp up and 4 of most of the stabilization and 3 of some of the ramp downs. So the reason it's a little difficult to tell from some of these plots is that this is all stuff that's a little bit ongoing, and depending on when the plot was made, you may see more or less data for a particular thing. So yeah, we've got 4 members. So we're not necessarily covering a huge range of internal variability possibilities, but you see there isn't an awful lot of difference. So a lot of this is forced response. You can see that there isn't a lot of difference between those ensemble members that we've got. We get changes in timing of maybe a few decades between some of the tipping events across the ensemble we have.
And this one is from Gabby. What do sea level rise spatial patterns look like at, for example, 3 degrees of warming?
I don't know. We haven't looked at that. I said most of it comes from Greenland. What we haven't done with these sort of simulations is done really any of the solid Earth stuff that would affect those regional patterns. So we've got a mix here of, we've got regional input from the 2 different ice sheets. We've got a bunch of thermosteric stuff. There's a little bit of circulation change. So all of those things feeding together make quite a complicated picture, and I wouldn't like to speculate.
Okay, thank you. We have time for more
Sorry,
questions. Okay. Johannes, do you want to?
Thanks. Thanks, Robin. This is really interesting stuff. I have many questions. Maybe I ask them most after the session.
Sure.
But my main one would be about the ice shelf front. You mentioned that you sort of pin the ice shelf to its present day position. So that means you probably overestimate the buttressing in your projections.
We pin the carving edge, so the very surface. So the thing we can't change in the model is the land sea mask as it runs. So we can let it thin and we can let the grounding line go back. And to be honest, getting the thinning is probably the biggest part of reducing the buttressing. Yes, potentially it might be a bit of an overestimate, but I would worry a lot more about the initialization, to be honest.
That would be my second question.
Okay.
Did you do you did an inversion for present day conditions?
Yes.
So basically present day geometry, but and present day trend.
Yes.
So is some of the sea level signal also due to Thwaites Pine Island retreat, which then affects also the Ross and the Flechtner-Ronne sector? Or is it driven by Ross and Flechtner-Ronne mostly?
All right, so the nasty and complicated plot to explain, which I didn't have in the main body of the talk, is this one on the right here. So this is the total sea level response, or this is the total mass loss, so the sea level increase is going down, if you see what I mean. So just looking at Antarctica as a whole, this dotted line, this control one that has the most, that is the one, that is entirely this West Antarctic thing going on. It doesn't we think, so the thing that's going on in the Ross sector particularly is very clearly a force signal. I haven't got the other plots. If we do sort of basin by basin or sector by sector for the things, you can see the West Antarctic is this constant background thing, and then right at the end of the simulation, in all of the simulations, it takes off once it hits a certain point. Whereas the other simulations, that background is there in all of them, but the Ross and the filter running are doing sort of independent, much bigger things, depending on the timing of the forcing.
There's another question on the back.
Thank you. Thanks, Robin. So the sea level rise thing always gets me, how long the timescales are for sea level rise after we've finished the forcing. I'm guessing you were showing the ice sheet contributions alone, or was that also thermal expansion?
That plot is ice sheet contribution alone. That plot doesn't look any different when you put the thermal expansion in, because it's in global warming levels, so it doesn't have a time component. So the thermal expansion in these simulations is the bigger component to start with. Particularly for the warmer ones, it does get to the point where the ice sheets are outweighing that thermal expansion term, yes.
So just to be, so in terms of the commitment, is it much larger when you include the thermal expansion, the overall commitment to, say, stabilizing or ramping down?
Yeah, and it's probably double, I should think.
Okay.
What was on those ones?
Yeah, fascinating.
But I would take a lot of the, I'm quite happy to believe in the physics, I'm quite happy to believe in the direction of these signals and a lot of the interactions. I'm pretty skeptical about taking actual numbers for rates and how much you get at a particular time out of this thing. Like I say, a lot of that does depend on the initialization of the ice sheet.
Maybe one more question? Yes?
So hi, I'm Richard Wood from the Metals. Hi, Robin. These are really impressive results. I have a question about your statement when you said that for the warm water intrusion under the ice shelves, that because of model biases, you couldn't necessarily use this as an early warning. But the physics of that is quite robust, isn't it? So you could presumably, in principle, if you're measuring the density, you could detect that that tipping point had been passed. And in terms of early warning of the actual impact in terms of sea level, then you probably have got
Probably, yes. I mean, I think we're happy enough with the physics.
I mean, what's the time scale once that tipping point's passed to actually seeing the sea level impact?
To seeing the sea level impact, well, all right. So I mean, in this case, you're still looking at sort of century scale for sea level impact. I mean, you could certainly look at the density. You could do a good enough job of measuring the density of the water in front of off the continental shelf and on the continental shelf, and the trend, I think, to see extrapolate linearly when it was likely to go, turning that in, and then once it goes very quickly. You get that once the melting starts very quickly, then saying how much that melting is and how quickly that turns into a dynamic contribution, that's going to be a much more model-dependent thing.
Yeah. Okay, but at least you've got some warning that something's about to happen.
Yeah.
Okay, thank you. I think we need to move on, right? Okay, thank you, Robin. Thank you very much. So our next talk is by Johannes. Yeah. Antarctica's inner values, tapping Antarctica's subsurface to project its future evolution.
Hi, everyone. Very glad to be here and talk about one of my favorite topics, the internal stratigraphy of the Antarctic ice sheet, and what we can learn from it about past evolution of the ice sheet and future evolution of the ice sheet. I'm also very happy that Robin also introduced already the basic concepts, so I don't have to go much into the details there. A little warning, this presentation will have a lot of videos. If the contrast doesn't work, apologies in advance, but we'll try our best. So, that's the wrong direction. This is the right direction. If we talk about Antarctica and tipping points, we mostly talk about the marine ice sheet instability, right? And just to quickly reiterate the concept, if we look at the bathymetry of the ice sheet or the topography, then the marine ice sheet instability mostly is situated in areas where the bedrock is underneath sea level and slopes down as you go towards the interior of the ice sheet. And the simple reason is that as you retreat the grounding line, perfect. If you retreat the grounding line into the interior, the ice thickness increases, and that's why the discharge also increases. And this is a self-sustaining feedback mechanism, which is then potentially irreversible on human timescales. Robin also mentioned already that there's a lot of processes involved in the evolution of the ice sheet. And you have the atmosphere impacting the surface mass balance. You have the ocean impacting the ice melt underneath the ice shelves. And you also have the bedrock, very importantly, which rebounds or is pushed down as the ice sheet changes in ice thickness. So there's a lot of uncertainties in these modeling attempts as well. And one of the uncertainties is, of course, scenario uncertainty, which is not too bothering because this is a fact in all Earth system elements. And as long as uncertainties are rather small, we can just cover all these scenarios and project sea level. More concerning is GCM uncertainties. So as Robin said, the ice sheet doesn't really care about global mean temperatures. It mostly cares about, for example, how warm the ocean and how salty the ocean underneath the Pine Island, Thwaites ice shelves is. And here you see an example of MIT GCM. That's a publication from Sebastian Rosier, where they ran an ice sheet model forced by MIT GCM, which is this solid line here. And in the background, the thin lines are basically the forcing which is used in ISMIP 6. So these are vastly different. So it could be that you have one GCM which is run for worst case scenarios, which has the same temperature anomaly underneath the Thwaites Glacier, like a RCP 2.6 scenario, for example. And then it's really difficult to make statements on sea level projections. And the uncertainties I care most about are the ice sheet uncertainties. So this is a publication by Helene Srusi from last year, which shows really nicely in the bottom part the percentage of ensemble members which unground under a certain forcing. So all the areas which are red, there the ice sheet models agree on the grounding line retreat. And this is in this case mostly because these parts of the ice shelf or the ice sheet are so close to flotation that all the models pretty quickly do the same thing. But in the other areas, all the models very disagree on different scales, right? So in the ice sheet model uncertainties I want to talk about because they produce these big spreads here. So this is a plot which shows the Antarctic sea level contribution if you just would expand the current trends. And the bottom lines here are different ice sheet models which do projections. So on this plot, it seems they all underestimated the sea level projections. But it's a very complex discussion. And one of the biggest complexities here is how we spin up the simulation. So we basically have three different options here. One is that we invert for present day observations. So here you see a nice example where Sebastian Rosier basically inverted basal conditions to match the present day observed thickness and velocities. So this gives you the perfect ice sheet geometry, the perfect driving stresses and perfect grounding line position. So you're well situated to project what the ice sheet does in the future, but it kind of ignores the paleo imprint of temperature on the ice fabric and rheology, for example. And then you can take the generalist approach, where you assume that the ice sheet is in equilibrium with pre-industrial forcing. So you basically run the ice sheet into a steady state, and from there you do the projections. But then you have the issue that the surface elevations, so your driving stresses, your surface gradients, and the grounding line are not as observed today. And then you have the third option, which is paleo spin-ups, where you run the ice sheet over several or one glacial interglacial cycle. And this means you have the ice temperature in a very good agreement with ice core observations, for example, so reconstructions of borehole temperatures. But your grounding line will be all over the place, and the surface elevation won't match present day either. But I want to sort of advocate for these paleo spin-ups because you have something which is called isochrones. And here you see a radar transect across the ice sheet. So the vertical, the y-axis here
is the depth or the elevation, a two-way travel time, which you can translate into an elevation. The basal reflector is the bedrock geometry. And in between the surface, which is at 0, and the bedrock, you have all these fine lines, which are isochrones. And these isochrones are layers of equal age, which have been deposited by snowfall sometime in the past. So what you look at here is basically 200 or 400,000 years of climate history encoded in the geometry. I have to find my mouse now. So we're now going to travel along this transect, and you will see how these isochrone lines will drape over the bedrock, kind of. So they're basically formed by ice flow and by basal conditions. They're going to quickly stop this here. So basically the surface mass balance affects the thickness of these layers and the thinning function. Then the geothermal heat flux and basal conditions like melting and freezing will affect the shape of these isochrones. And the flow is basically imprinted in the geometry. So in theory, if you could uncover the concepts behind or the mechanisms behind this isochrone geometry, you would basically have the key to past climate changes and past ice dynamic changes. So that is kind of the idea of isochrone calibrations. And with regard to data, where can we compare ice sheet modeling with isochronal data? The colored regions here show basically regions where we have these radar lines traced and dated, which means we know the age of the isochrones and the geometry. And the most prominent feature of this is probably the empty gaps, or the things where we don't know anything. But you see that for the ice divides at ice cores, we have a pretty good coverage already. And we're working currently on the coverage also in these marine basins to constrain ice dynamics. So if you have an ice sheet model, you can run it over glacial interglacial cycles, actually. Handing the mouse again. So this is basically one random simulation where we simulate the Antarctic ice sheet over 120,000 years. And what we do here, we use either Lagrangian tracers or an isochronal model to simulate these internal layers. So basically with our model, we advect the ice and create these isochronal surfaces along the model simulation. And if we have done that, we can then go towards the data and compare the geometry of the isochrones with the observed geometry which we find in the radar data. And the mismatches between them give us an idea about biases in the model, biases in the surface climate evolution, biases in the basal conditions. The challenging thing here is that this is a really wicked problem, because here you see an example of a borehole temperature at dome C. So this is the dashed black line. And all the other lines are basically attempts with a model to match this black line, where we vary surface mass balance, geothermal heat flux, rheology, etc. And this is just one selection of runs, and you can see that in the default assumption of a climate index simulation, this line here, we are way off the chronology. But then we can improve this chronology and map it onto the observed one. And we actually by now got much better until the year 600,000 before present. We have a pretty good match, and then we deviate probably due to basal processes in the ice, which we cannot resolve. The issue here is that you basically, if you wiggle on the surface, you also affect the results at the bottom. If you wiggle at the bottom, you affect the results at the surface. So it gets really complicated, but for an ice core, we have managed to basically find good settings. Where it gets more complicated is if we go towards marine basins, such as the Wilkes subglacial basin, which you see here. This is an area in East Antarctica, which is about the same size as the West Antarctic ice sheet. And if we would have a collapse here, we would contribute around 3 to 4 meters to sea level. So ballpark the same as the West Antarctic ice sheet as well. And in our group, we have created some isochronal data, which covers some of the outlet glaciers in these basins. And the main glaciers here are the Cook Glacier, the Ninnis Glacier, and the Mertz Glacier. These basically moderate ice flow in the region. And what I want to show now is model representations of these regions and simulations from 130,000 years until present. So in white, you see the surface elevation. In green, bluish, you see the bathymetry on the continental shelf. And then white here, you see basically the radar transects along which we have isochronal data. And if I remove the surface, you see the bedrock bathymetry underneath. So maybe to orient you, these darker blue areas are the glacial troughs where we have retrograde bed slopes. So along which we have a retreat of the ice sheet, or could have a retreat of the ice sheet. The white line is the present-day reference grounding line, and the red line is the model grounding line, in this case at the penultimate glacial maximum. And they're going to now run the simulation from the penultimate glacial maximum until present day. This will be a very fast movie, if I can start it. And maybe I run it a couple of times because things will go really quickly. So you have a collapse of the ice sheet, you have a rebound of the bedrock, and this was 20,000 years. And then the advance of the ice sheet comes back. We go towards the present day. So up here you see the time we are. So we end up somewhere in the Holocene where we go back to the current grounding line. And if we repeat and you focus on the grounding line at the beginning of the last interglacial, you see that the collapse is initiated at the Ninnis ice stream and at the Mertz ice stream. And then it gets really quick, so just a couple of thousand years. That was too fast. So we collapse the ice sheet, and then the bedrock can rebound. And as it rebounds, you form little islands where you can form new ice cover, and then the ice sheet advances again. And the interesting thing here is that we want to look at the isochronal imprint of such a collapse. So what you see here in these dots is basically the ice which has been deposited 120,000 years before present, and where we find it today. And what I'm going to show now is how this ice got there in this simulation where we have a collapse of the basin. So really have trouble finding the mouse here. So if you focus on the colored dots, you see that at some point in the past, they're deposited, then they accelerate with the collapse, then they decelerate with the regrowth, and they approach sort of their final position where we observe them at present, right? So they slowly march towards the present day position. And the interesting thing is now we can run different scenarios where the ice sheet collapses or where it doesn't collapse, and this will lead to different positions of these dots, so basically of the tracers. And then we can compare the isochronal geometry in these areas and figure out whether a collapse scenario works better with these internal layers or a non-collapse scenario, calibrate the parameters, and then run projections with it, right? And this is the moment where, in theory, we think the ice has been deposited, and in a collapse scenario, the configuration of the ice sheet would have looked like this, right? And if we look at the velocity at any point somewhere between dome C here at the top and Talos dome ice core here, you see that in case, so on the y-axis you see vertical velocity, average vertical velocity. The collapse leads to a strong acceleration and then a deceleration. And the stable simulation leads just to a little acceleration during the last interglacial and then a steady flow. So actually we have an acceleration and a deceleration in the collapse scenario. And this then leads, I don't know, 1 minute, okay. This then leads to an imprint on the isochronal geometry. So this is basically an across flow transect, where in red we have the observed isochronal geometry, and the other lines are basically model geometries where we simulate the different ages of the ice. And you see here, these lines are basically the model suggested elevations of the isochrons. And depending on the model simulation, there are different positions, and then we can optimize for that and figure out the scenarios for different areas. So my conclusion is, all these different approaches, whether you take a paleo spin-up or an equilibrium or an inversion, it kind of depends on your approach. But if we want to do isochronal calibrations, we have to take the paleo approach, and I think it's a very nice method, because you have all these different paleo surfaces with which you can calibrate your model. So not only present-day geometries, but also paleo geometries. And we can then also translate this into future simulations, which I won't show here now, or I mean, I can just play it. So this is an example of the region with the UK ESM model of one specific configuration where the ice sheet was stable in the last interglacial, and in the UK ESM forcing, it is destabilized over the centuries. This is a run until the year 3000. And now we are running different simulations with different assumptions and compare then the isochronal mismatch to figure out which scenario is the most realistic. Thanks.
Thank you. Thank you, Johannes. I think in the sake of time, we're going to go on with the other talks. Okay, so there's an online talk now by Jorge Bernales. It's on Greenland. Let me check. The fates of the Greenland ice sheet under the idealized scenarios of the TipMIP ESM protocol as simulated by ECR ESM.
Yes, can you hear me correctly, Erika?
Yes.
Yes.
That's perfect. And people are now seeing my shared screen, right? Not the one that you are you were showing on your own monitor.
It's good.
Okay, so let's see, change perfectly. Okay, I will start now in the interest of time. So, well, thank you a lot for having me here, and apologies for not being there. I will repeat what previous speaker said, that it's really a pain not being there, but I hope you have a nice day. And thank you a lot to the previous speakers, because they will save me a lot of time introducing certain topics. So as Erika said, this is the title of the presentation. I am the first name here. I hope you can see my mouse there. This is with Cheng and shooting, but we cannot do this alone, of course, and we have to thank and to credit the entire Easy Earth consortium, because this has been a huge work done within this community. And also I want to thank Robin, because he donated one slide on the Greenland stuff, so I can present it as well, more or less to show a comparison between our experiments using the coupled Easy Earth 3 Earth system model and UK ESM. So I will start right now. You already saw this diagram. This is from the TipMIP protocol. Shooting explained it very well at the beginning, so I will not go into details, but just in case, to refresh the memory, I will say that here basically we go from a pre-industrial control simulation, which is the black line. That's our reference run under this constant climate. And then we start running ramp up simulations that go up at around 0.2 degree per decade. After that, we stabilize the simulations at different global warming levels. In this case, you can see here the 2 degree and the 4 degree ones. And after 50 years, we use the ramped down, trying to get back to the pre-industrial climate. I won't go into the details because this has been already presented before. Now, how does it look in our simulations, from our results, from our output data? This already was shown, but this is how it looks. So you have the control run at the bottom, this gray flat line. You have the ramp up ensemble, which is this run that goes up. And from this one, we branch out to different global warming levels. So we go from 1.5 degree to 2, and 3, 4, 5, and 6, so to say. These are still preliminary simulations and results, very fresh. So it will take some time and also a lot of computational resources to get this thing going for most of the branches. But I mean, this is preliminary results. So now, how does this one in turn translate into Greenland results? Again, this is a figure that Shooting shared earlier during her talk. This is a very complex plot. It's very packed, but this is the entry point for understanding all our results regarding Greenland. I will explain and I will walk you through this figure step by step, so don't worry about it. You don't need to read or understand every single detail here, so I know how it feels. But I just want to say that here you get the evolution of the Greenland ice sheet mass total, which is the y-axis. This is in gigatons. Let me move my the gallery here. On the y-axis on the left side, you have this total mass of Greenland and how it evolves over time, which is the x-axis. So it goes from 0, which is the start of the control simulation, and then it goes up to 500 years, depending on the simulations. Again, these are preliminary results. On the right-hand side, you have more or less the percentage change relative to the initial mass of the Greenland Antarctic ice sheet, so to the total mass. So if it's at 20, it's basically 20% reduction relative to the initial total mass. And it's way easier to understand this in terms of sea level rise. That's the red numbers there. So more or less, you can say that if you lose around 20% of your Greenland ice sheet, that's equivalent to more or less 1 meter global sea level rise, static sea level rise. But I will walk you, as I said, step by step. So I will move here. Let's start with the initial state. So with very extremely explosive Photoshop skills, I will just show you what's going on here in the control and the historical run. So that's the dotted gray line and the dashed black line, respectively. These are simulations that are run for around 200 years in terms of the control, and from the 1850 to 2014 for the historical run. Basically, what you see here is that the mass of Greenland for the control run is very, very near equilibrium under this pre-industrial climate. And what you see from the historical run is that just at the end tip, you see a decline in the total mass. How does it look, though, in terms of Greenland? So here you have 4 panels, and the one to the left is basically the surface elevation of the Greenland ice sheet at the beginning of the simulations. So this will be the control, more or less equilibrium state. And then what you see in the rest of the panels is how it evolves in the historical simulation. So every basic 50 years in this case. So even though this is the historical run where you don't see that much decrease in the total mass of the ice sheet, you more or less see the places where you experience thinning relative to the initial state. That's the blue spots, and thickening. That's the red spots. Those are mostly concentrated or focused on the ice streams areas. Let me change here. And this is a comparison of the last 30 years of our historical simulations and an observational compilation from the years that you see there. What you can see here is that more or less at the interior of the ice sheet, you see a slight underestimation of the ice elevation or thickness in this case. And in the red spots at the margins, you see in all these fjord areas an overestimation of ice thickness. I can come to that point later during the talk, what their implications are for this kind of performance. Now, what you see here is the evolution of the components of the mass balance of the historical simulation. In blue, you see the surface mass balance. In red, you see the frontal mass balance or the discharge. In this yellow-orange color, you see the basal mass balance, and in black, you see the total mass balance. So you can see here that until around 1940, which is around this 80-year mark, you see a near equilibrium Greenland ice sheet, and there a slight decrease in it, which continues more or less stable until around the 1990s, where you start seeing a decrease of the surface mass balance and therefore a decrease of the total mass balance. And this is something that you will see repeating in the next plots, because for Greenland, surface mass balance is king, and it dominates the evolution of the mass balance of the Greenland ice sheet. I also added here, well, this is in gigatons per year, but I added to the right the numbers in Sverdrups, in case the oceanographers there more or less want to see an equivalent in numbers that are more common in that community as well. Now, let's talk about the ramp-up simulation. So we started from these plots, and then now we add the ramp-up simulation here. This is how the Greenland ice sheet evolves from the pre-industry, from the control simulation over 300 years and this ramp-up range, the ramp-up simulations. As I said, these ones are simulations in which the global climate increases by around 0.2 degrees per decade. And you can see there is a strong decrease in the total mass of the ice sheet. So it's around 20% decrease at the end of the ramp-up simulation. How it looks in terms of 2D plots? Well, here you have the initial state, so the control run to the left in terms of surface temperatures. And you have here the point in time where we branched out for 2 different global warming levels. This is +2 degree and +4 degree. And you can see here that this is definitely more than 2 degree and 4 degree. This is basically polar amplification on the Greenland ice sheet, mixed, of course, with some elevation temperature feedbacks that are very, very important in Greenland. Even though you can keep more or less the global warming level constant at a certain degree, as soon as Greenland starts thinning, it will go down in terms of topography, and that will increase the temperatures, and therefore you have this positive thing that can spiral down. Now, in terms of, well, this is surface elevation, you can see more or less the points where it starts losing mass, which correlate more or less with the initial points I showed for the historical run, but these are on asteroids, basically. You have decreases of hundreds of meters in these areas, especially for the 4 degree of global warming level. And in terms of the mass balance components, here you have the ramp up ensemble. It's the same again, so you have the blue line is the surface mass balance. The red line here is the basal one. You have the frontal discharge in yellowish, and you have the total mass balance of Greenland, which goes very, very, very negative to around 4,000 gigatons per year, which is the equivalent to around 0.13 Sverdrup in terms of contribution and freshwater fluxes into the ocean. Now, after this ramp up, I said we will branch out at different global warming levels, and this is what you see here. Normally, if you recall the plot with the temperatures from the climate model, one of the first figures I showed from the results, you saw that it stabilized in terms of being a almost horizontal line. So here you have, that's not that case. Actually, you have a continuous loss of mass from Greenland, even though you stabilize the temperatures globally. It still continues losing mass. So this is what I mentioned about the surface elevation and temperature feedbacks. Yes, this is basically just to show that even though you are stabilizing the temperatures, they continue decreasing. These are panels relative to the initial point of the branch, just to show that it continues warming due to this loss of topography, this decrease in the elevation, which then puts up the temperature and enters this positive feedback. Same for the topography. We can see that in this case, for the warming level at 4 degrees, even though it's constant now in terms of temperature, the elevation suffers a lot. And this is just positive feedbacks again. We can see the mass balance components here, and you still have a significant loss of mass that is sustained over time. So the fact that this is horizontal doesn't necessarily mean that it's stable. It means that it keeps losing mass at a constant rate. So this showcases more or less the amount of mass that at this point the Greenland ice sheet is suffering. And finally, for the ramp up, the ramp down simulations, we can now complete the initial plot. Now we have these dashed lines that show that when you start going back to the pre-industrial climates, you see some recovery of the ice sheets for some global warming levels, not for all of them though. So you can see here that around the 3 degree level and the 4 degree level, you are not necessarily recovering. And this speaks to what Robin was mentioning before, that for societal timescales, you might not see a recovery of the Greenland ice sheet to the pre-industrial or at least initial levels, unless you go into colder than present climates for a very sustained period of time. This is what Robin donated to us is basically the equivalent from UK ESM. You see the same figure showing a similar result. And this is another type of plot to the right-hand side where he shows the evolution of the surface mass balance relative to the global mean change in temperature, showing basically that when you go back in the ramped up simulations, the SMB is reversible in a sense. Now, for those of you who like to see a lot of text in the slides, I don't have that much, but here is the summary. First of all, as Robin said as well, we see no apparent tapering behavior from the Greenland ice sheet, although we see a small evolution, which is dominated by these elevation and temperature feedbacks. And we see that the stabilization runs are unable to stop the thinning of the ice sheet, although there are signs of partial reversibility at certain global warming levels. Although we are not accounting for all the processes, especially subglacial processes like hydrology, that can tip the dynamics of the ice sheet, and that could tell a different story. So this is work in progress, and thank you a lot for your attention.
Okay, thank you very much. I think we will move on to the last talk, which will be given by Javier Blasco. I'm sorry because I forgot to mention all the affiliations, okay? So I will shut up now. On the Antarctic response to an annual 1% annual increase in atmospheric CO2.
Okay, can you hear me? Or no? I think. Yeah, now. Okay, more or less. Sure. this anomaly into ocean also precipitation increases following this Clausius-Clapeyron equation. So with a warmer temperature, we also expect more accumulation. So let's go to the first experiment and results. Here I am just showing the case with the lowest oceanic sensitivity, 0.25. And you can see on the first panel, left-hand side, the temperature where we are committing. And on the right-hand side, the oceanic temperature in Antarctica. The middle panel shows only the sea level contribution for the case with climate variability, and this noisy part reflects the sea level rise acceleration. Because if we see a considerable acceleration, this points us to a nonlinear response of the ice sheet and probably a messy mechanism. And in the last panel, I show the difference in sea level between the case with climate variability and the case without climate variability. So if it is positive, the case with climate variability contributes to a larger sea level response. So in this case, which has an oceanic warming of around 0.7 degrees, we don't see much response. We see that by year 5000, so in a 3000-year simulation, we have a sea level contribution at the end of 1 meter, and we don't see any considerable acceleration. If we go to the second and third case, we obtain a quite similar response. In this case, temperatures, oceanic temperatures have risen between 0.9 and 1.1 degree. But still, we don't see a considerable acceleration, but usually we do observe always a slightly larger contribution for the case with climate variability, rather than for the case with a mean climatology. However, finally, in our last experiment, which is committing to 4 degrees, which represents 1.8 Kelvin of oceanic warming, we do start to observe an acceleration around year 3500. And in this year, we start to see a considerable sea level rise contribution, which reaches more around 5 meters of sea level rise. However, interestingly, if we compute the difference with the case of climate variability and the case with a mean climatology, we see that the case with climate variability responds before. Later, it tends to converge, which points us that MESI is occurring before for the case spun up with climate variability than with a mean climatology. This can be shown here. Here I'm showing the grounding line position. On the left-hand side, climate variability spin up. On the right-hand side, the mean spin up. And the green line represents year 3000, the blue line year 4000, and the red line year 5000. As you observe, by year 3000, we have relatively a similar grounding line position, although a slightly more retreated in the Amundsen Sea event. However, this slight retreat tends that by year 4000, we also already have a collapsed West Antarctic ice sheet in the case with Antarctic climate variability. Whereas in the case with a mean climatology, the grounding line is still more advanced and we don't have such a big sea level contribution. This explains this large gap between these two cases. Finally, I will just go to the study to a study of the oceanic sensitivity. Again, left-hand side represents case with climate variability, right-hand side case with a mean climatology. Upper row year 4000, lower row year 5000. So the x-axis represents the global atmospheric anomaly, which goes from 1.5 to 4.0, and the y-axis represents the oceanic sensitivity, which goes from 0.25 to 0.5. So this means that as we go right and up, we increase the oceanic warming. The colors represent the Antarctic extension, the West Antarctic extension. So red colors represent a collapsed West Antarctic ice sheet, whereas blue colors represent a grounded West Antarctic ice sheet. The numbers inside represent the oceanic anomaly as seen by Antarctica. So as we see, as we increase global temperatures and oceanic sensitivity, we tend towards the redder colors. Whereas if we go to low sensitivities and low atmospheric warming, we tend towards the blue colors. So we don't measure any collapse of the West Antarctic ice sheet. However, there is a case, which is the 1.35 degrees here, the 1.8 degrees, where in some cases you can see it has collapsed, and in some cases you can see it has not collapsed. So I will plot it here now. You can see those squares. Now what I'm plotting here, again for upper row is the year, lower row the year 4000, lower row the year 5000. And what you can see in the x-axis here is the oceanic temperature, and on the y-axis the ice extension of the West Antarctic ice sheet. So we see that for low oceanic anomalies, we have quite a big ice extension, whereas for big oceanic anomalies, we have a low ice extension. But then we are inside this region, the 1.8 K region. In this region, it's interesting because some cases they have a larger ice volume and others have a lower ice volume. The scatter plots, which are thicker, represents those which have more accumulation. So we see that accumulation can be an effective mechanism to avoid a collapse of the West Antarctic ice sheet, although we can be inside a temperature range which could lead to a waste collapse. So I think with this I will finish. I think the main idea you should take is taking into account climate variability leads to a faster response of the ice sheet in our case, and the other, well, that precipitation in some cases can delay the response by some centuries. Nonetheless, this is an idealized work. We still need to evaluate this with Earth system models, and we still need to evaluate this, how Earth system models simulate polar amplification and also precipitation increase. So thank you.
So thank you very much, Javier. So I guess it's time for questions now, and I guess we will start with the ones online, right? Okay.
Yeah, I mean, it's probably better if the speakers all come down.
Okay. Oh, okay. So the speakers can come down.
Oh, okay, so. We have some online questions. No?
Okay.
Okay. Any questions in the room? Right, Didier?
Yes, thank you for those interesting talks. I was wondering...
Can the questioners introduce themselves, please?
Yeah, sorry. So I'm Didier Svingodo, CNRS France. I was wondering, for those who have done historical simulation, how the sensitivity, the ongoing melting can be compared with observation. Have you looked at that somehow? Is the simulated loss of mass larger than or lower than what is observed? Can you comment on that? For the historical, so not this one, but for I've seen a few of them.
I don't know if we can go back to one of these. This is a plot of sea level rise potential of this certain region where I modeled or I presented. And this goes from 200,000 years to present. And if you look at the last part, you see that kind of the sea level volume equilibrates. And we try to match the basal melting underneath the
Okay, I just would like to point out, we try to match by calibrating the model to have basal melting rates as close as possible to observations. However, having basal melt rates as close as possible to observations doesn't necessarily lead to a good Antarctic ice sheet, because at the end there are more uncertainties related to ice sheet models. So at the end, depends where you want to tune a bit. If you want to tune for a realistic present day geometry, maybe you also need to modify melting rates in order to obtain a good state.
here or?
Thanks for the talks. Johannes, I understood correctly. I'm Jorge Álvarez Solas. I come from Madrid. I work on ice sheet modeling as well. So, if I understood correctly, you were saying that the simulation that matches the best the last interglacial was the one with the wheels collapsed. Is that correct? Is that one matching the isochrones better?
So we're basically still trying to figure that out. Because the one video I showed you, I tried to show that if the Wilkes basin collapses, you have an intermittent acceleration of the ice flow due to the grounding line retreat and more sliding, etc. But as the Wilkes basin builds up again, you have a deceleration. So you have these antagonistic effects which lead to the fact that the isochronal geometry in both cases is very close to each other. But you have some sections which can indicate a collapse or not, and currently we can definitely rule out a complete collapse, but we're trying to pin down more the degree of collapse, actually. Yep.
Thanks. And I have another one for Robin, if I may. You didn't say anything about the AMOC in your simulations, but I didn't get whether you put in the water from Antarctica in your climate model on, or is unplugged, or is it the changes in the mass of Antarctica translated into meltwater into the ocean?
Absolutely, yes.
Yeah.
Anything coming off the ice sheets is going into the ocean.
So it's fully coupled.
I hate that word. It is coupled in that sense, yes.
Okay.
And there's a distinction between meltwater and solid discharge. So we have icebergs that can float around and melt. Whether there is an impact on either the ACC in the south or the AMOC in the Atlantic is, I think, an open question that we need to look at. Clearly, those things change in our simulations, but there's a lot of warming. There's a lot else going on as well.
Thank you.
All right, Torben is next.
Yeah, Tom Koenig from Messenger in Sweden. I have a question to the statement that there were no tipping point behaviors in Greenland. So both you and Georgia showed that there is, after warming of 4 degrees or so, that the melting is continuing even if you go back to pre-industrial temperature. Isn't that the sign that a tipping point has been passed in time, although you don't see an abrupt collapse or something like that, similar to the behavior you might have seen in Antarctica?
Jorge, do you want to comment? Are you there?
Yeah, I'm here. Could you please repeat, Robin, the question, because I cannot really completely hear it from the audience there.
Shall I repeat it, or better, Robin, because...
So the question is asking whether we're sure that there's no tipping behavior on Greenland. Because even as you start to cool down from the higher temperatures, it still looks like mass loss is continuing regardless.
Yeah, I remember the kickoff meeting of TipESM where we struggled to find a common and agreed on definition for what a tipping point or tipping element or tipping threshold, whatever is. So it is. We don't consider it a tipping behavior in the sense that it's not a sudden change with explosive, say, contributions to sea level rise. But yes, you are right in the sense that you have potentially a runaway effect in Greenland because of these positive feedbacks. And now, whether that qualifies as a tipping point crossed, I think that's up for debate. But yes, you are right in the sense that hysteresis is definitely there for some warming levels. I think Romy will agree on that. But it's very smooth and is at points even linear. So yes, you have that there.
I mean, I would be even less sure than that. So yes, you still get loss, but it maps really closely onto that global warming level. It doesn't. It's still losing because even though you're reversing from 6 degrees, you're still at 4 degrees warming, and you're not going to start building up the ice sheet again until you get. You're not even going to start building it back up till you get back to 0, and then it will take
thousands of years. Jorge's right, it depends on what you call a tipping point. And I would, it's also worth looking closely because I think there are individual outlet glaciers that do start doing nonlinear things that maybe aren't reflected in that whole sort of Greenland-wide budget. So there is stuff to look at.
Yes, and I just want to stress the last point at the conclusion of my presentation is that the fact that we don't see these sudden changes and they are mostly smooth in our simulation doesn't necessarily mean that there are no tipping points in reality, because there might be processes, especially those related to ice dynamics and subglacial conditions, that can actually change completely the picture once you introduce them in a physically based way.
Yeah, absolutely. Sorry, Colin was next. And
Yeah, a question or comment for the last speaker. So as I understood it, your Antarctic amplification was kind of fixed in time, and your fraction of ocean warming relative to surface warming was also fixed in time. At least I didn't introduce myself. So I'm Colin Jones, University of Leeds, at the Met Office and part of the UKSM team. And that's relevant. So in our UKSM runs, in the zero emission runs anyway, that fraction for Antarctica would change with time. And that's because all the accumulated heat through the ramp up and everything starts to reappear with ocean circulation in the Southern Ocean. So the Southern Ocean gradually warms from depth and then it warms upwards through the column. So I think you could probably mimic what that fraction should be with time if you looked at some of the Earth system model simulations. And you might find that 1.8, I think you had 1.8, didn't you? Would go from 1.8 to maybe 2 point something. And even the fraction of ocean relative to atmosphere might change as well. And that would have a big impact probably on the sensitivity of the ice sheet in the stabilization runs. I don't know whether you tried anything like that.
No, I mean, our first approach was to apply homogeneous warming because it allows also to have a homogeneous warming over the whole Antarctica. The idea is also to evaluate with ESM. Nonetheless, having a polar amplification which changes in time would be interesting to test in our experiments. I guess also if we take different Earth system models, this changing will change a lot in Earth system models. So at the end, it is a source of uncertainty within our projections. But I agree, I mean, for a first attempt experiment, it would be interesting to see also. Because, well, I don't know if it should increase or decrease actually in 5,000 years. But, yeah.
I'm talking about centuries, not...
Oh, yeah, okay.
In centuries, in our model, it definitely increases.
Okay, okay.
Okay,
okay. Yeah. Yeah, it would be interesting to know those numbers by even also oceanic warming in different basins from Earth system models so we can compare because we know this will play a big impact in Antarctica. Thank you.
One last question in the room and then one online.
Michael Gill. I held in this room a meeting some years ago for a whole trimester on mathematics for the environment and climate. The previous question, not this one, the one before, about what tipping is. It reminds me of Bill Clinton, saying, it depends on what your meaning of the word is. We're having here two projects important and who do terrific work. But the fact that nobody really worries about what is meant by tipping point. There are basically two approaches. One is to strike fear into the beholder, Tipping is something when something terrible happens. When you read Malcolm Gladwell's book, or you don't read it, you just leaf through it, it's just incredibly vague. It's a journalist, it's not a scientist. But then even within science, there is a point of view that the tipping point is not a point, it's a threshold. Well, it can be a separating surface in I don't know how many dimensions. It would be nice if people are really worried a little bit. There's another approach that is taken by people like Pete Ashwin or Christian Kuhn or even myself that a tipping point is a generalization of something that is more polysyllabic, but we know exactly what it is, namely a bifurcation point. And it's a generalization of a bifurcation point to non-autonomous dynamics. You know, what Stommel and Lorentz and Veronis and others did, that was for autonomous systems in which there was no time-dependent forcing. You know, forcing and coefficients were constant, okay? And so people understood pretty well. I mean, if you learned a little bit of mathematics, you knew about the different kinds of bifurcation points. Now, some of us also are trying to find out what all the possibilities are in non-autonomous systems. But there's not a lot of contact between people who worry about the definition and people, you know, who just do numerical experiments and then say, oh, you know, I think this is a tipping. Maybe it is, maybe it isn't. It depends on how you define it, okay? So I think it would be important to discuss what it is. It reminds me also in this meeting that this semester or trimester that I had here some years ago, we had Martin Clausen, who was for many years director of the Max Planck Institute of Meteorology in Hamburg. And he said, you know, science is about objects that are well defined. A good definition going back to antiquity is genus proximus et differentia specifica, depending how you pronounce it in your own language. Okay? So it's something more general that everybody agrees upon, and then there's a difference from the generality which defines it. So it would be good to think a little bit about tipping points in that sense.
Thank you, Michael. I should note that there is also a point from Tim Lenton online, also querying the speculations on how we're defining tipping points, what the important ones are. I don't think it's necessarily fair to ask the ice sheet people up here to take on that task. But it's a thing we should certainly think about and clarify at a project level, I think, would do no harm. Right. And with that, I think that's the end of this session. Thank you, everyone. It's time for a break.
In the same room, right? Yeah, so we have a coffee break until 4:10. So we are resuming at 4:10, so please be back here by then.
You're live now. Okay. And then you can use this and just this to go through your slides.
Yeah, perfect. Thank you.
No worries.
Sorry, I will have to make a short announcement.
So it has been very hard to fix this here. I can't take it off.
No, but I will take this one.
Good. That doesn't count as my time.
No.
Hello. So I have a few announcements to make. First, about the dinner tomorrow. So I forgot to say that probably they will require you to have an ID card.
Okay, so tomorrow don't forget to take your ID card with you. Just to go in this tower, in the Zamansky Tower, you will need an ID card, most probably. So a second thing is that the building here is very nice because everything is open and anybody can enter and go out. So the drawback is that you should be careful with your computer in the room. So if either you don't leave your computer in the room or you make sure that someone stays in the room. Okay, so thank you for this point.
I also have one, if that's okay. Sorry, I also take one announcement. For the registration sheets that we ask you to sign at the entrance, I think that goes for both projects, if I'm not mistaken, please actually leave your signature, not just a tick mark that you're attending the event. So we need your signatures for all days that you're attending the conference and the annual meetings of the projects. Thank you. I think ClimTIP has their own signature form, no?
He's online.
Okay, well, there you go.
Hello, hello, hello. Okay. So welcome back, everyone. I hope you enjoyed the coffee and the colorful, sweet food. We now start the next session on biosphere. So we're talking about from the Amazon to impacts on people. My name is Lucas. I'm a postdoc at LMU Munich. I'll be chairing this session together with Stephanie from PIC Potsdam. And the first talk is from Julia Pongratz, who is a professor at LMU Munich, the lead of the chair in physical geography and land use systems, and my boss. So, so go on, Julia, the floor is yours.
Thank you very much, Lucas. So the study I'm presenting is part of the PhD work by Selma Bultan, who unfortunately cannot be here. But there's other people from ClimTIP involved, like Sebastian Battiani, Niklas Börs, and also Lucas, in a sense that Lucas himself is doing complementary work. We'll come to that in the outlook. So Amazon forest decline is driven by both climate change and land use change. For some, this may be boring, but for those with all the ice sheet, I was very happy when there were some general slides about why these ice sheets matter. So maybe for that community, what I'm presenting in the first few slides is interesting. So a few quick facts on the Amazon. There's tropical rainforests, big systems in the Congo and Southeast Asia, but the largest one is the Amazon with 5.5 million square kilometers. It has huge impact on the hydrological cycle, on climate. It provides around 20% of the global river inflows to the ocean, the Amazon River going through the basin. A lot of the precipitation there is recycled. In a sense, it's coming from the ocean and then taken up by plants, evapotranspirated, and then rains down again, around 30% of that. And this is a key trigger for why the system could be a potential tipping point, or could be a tipping system. There's a whole lot of carbon there, mostly in the vegetation, but also a bit in the soils, 150 to 200 petagrams of carbon. So comparing that to the annual CO2 emissions from fossil fuel burning and deforestation being 11 petagrams of carbon, you may say, well, this is just 10 to 20 years of current anthropogenic emissions. So it may not be that bad, but it's really bad when you continue. Well, the Amazon rainforest hosts more than 10% of the world's known species, many unknown ones, really valuable for pharmaceutical research and so on. And it's under big threat. So from the media, what you know foremost is land use change. You know these famous fishbone patterns that walk in, I think I'll leave that go into the rainforest and start eating it up. Currently around 70% of the Amazon rainforest is already gone. And the Amazon, but all tropical forests in general, are really key players to local, regional, and global climates. They alter the surface properties, albedo, roughness, and so on. And also, of course, via the carbon, but also via downwind effects, could have large-scale impacts on global climate. So the Amazon rainforest is deeply stressed by climate change. There's many studies who have investigated that. Just 2 examples here. So the first study is by Brinen. They compiled more than 300 inventory plots, so intact forest, and then looked at how the forest evolved over time, and they found that the mortality is increasing, and with the biomass data that could show that the carbon stores there are lost. So that's increasing, and particularly bad in the Amazon, less so in other tropical forests. And another study here by Chris Bolton, they looked into statistical measures. So the leg 1 autocorrelation is a good measure to show how sluggish a system is and how resilient the forest may be. And they find, looking into remote sensing data of the vegetation optical depth, that indeed the system may become less resilient over time because this indicator goes up. So that's worrisome. Climate change impacts the Amazon. But what is not covered that well in science, only in the media, is that land use change also affects the Amazon rainforest. So first, deforestation is the main driver. You see here all these pink areas that have been deforested over the past. We're moving in from the Cerrado region ever further into the core rainforest. A lot of that is driven by export to other countries, in particular soybean production, but also cattle ranching that's exported to China and to Europe and the US. So there's a big lever we have in our hands here. And you see this depends a lot on the political evolution, of course. Lula da Silva brought it down to 1/3 of the deforestation. With Bolsonaro, it went up again. Now with Lula da Silva again, we need to see how this evolves in the future, but it's still a big threat. But it's not just clear-cutting forest to put cattle there or soybean fields, but there's also this presumably more subtle degradation. So in that study that David Lapola led, we compiled all the other effects that are there, the degradation. So a forest may remain a forest, but it's degraded. Why? Well, because there's a field next to it, and then there's this edge effect that the forest edge dries out. There could be fires going through that can be anthropogenic or climate change driven, logging, timber extraction, and so on. These are all things where humans have an impact. And in the recent years, when you've seen also last year's coverage of the Amazon rainforest, all this burning, that was particularly for degradation, or it led to degradation, not to deforestation. It was fires escaping because it was so dry there in the last year. Good, we want to change that, and you know the Glasgow Declaration that said we want to end degradation and deforestation by 2030 worldwide. And this is not quite the path we are taking. In the Global Carbon Project, every year we have this global annual carbon budget. We compile the emissions. This is now for Brazil, not just the rainforest, but the entire Brazil. And you see there's different estimates around of how much carbon the ecosystems by land use change take up or release. You see there's a big flux of around 1,000 megatons of CO2 when you take the average of those 4 models. It has come down with the political changes, but it's recently going up again. So it's clearly not that path of the Glasgow Declaration yet. So I hope I could convince you we need to look into land use change as well in addition to climate change. But there's few systematic quantitative studies that look into the relevance of land use change, such as deforestation, in the tipping point debate. Typically, when there's quantitative studies, they exclude the land use change because it makes the analysis easier to just focus on the natural responses than when you don't have these confounding effects. And therefore, we believe it's likely that we underestimate the threat for abrupt changes and critical transitions because we've so far typically considered climate change only and not the land use change on top. So clearly, that's what we would like to do, and there have been indications that when you take both together, again, these are semi-quantitative studies only, so not the clean ones we'd like to propose. So there have been statements about there's going to be, or could be a tipping point reached in the Amazon rainforest. It could move to another stable state that's then more savanna-like. And also the media picked it up, in particular when it's these dry years where even the natural forest for a few years already turns to a source of carbon. So this is what we investigated, what Selma Bultan led so bravely. She wanted to see how the disturbances in the Amazon rainforest are influenced by both climate change and land use change, and then see if there's an increased risk of forest dieback and a risk of transition to savanna. And the problem is there's big uncertainties about, do these tipping elements exist? What are the thresholds for it, for climate change, for land use? And so to get the best data we currently have on these uncertainties. So we investigate climate change, land use change separately in a combined way, and then we also investigate whether the changes that we see in the forest cover over time, whether they occur gradually or abruptly. If there's an abrupt change, that of course has very different implications for societies and for the ecological resilience. So that's also very important. So the methods that we applied there was, we went to the CMIP6 database, because there you have plausible scenarios of future evolution of both climate and land use change. And then we used those. So, and it's also Earth system models that have a high complexity, that presumably have many of the relevant processes in there, because there's also studies that use lower complexity models that have a big value for conceptual understanding, but maybe less realistic. But we can discuss the realism of ESMs afterwards. And we chose 4 models. Why? Well, because we chose those that have dynamic vegetation biogeography. So where forests can grow or can die because of climate change impacting it. And that's only 4 models left. All the others had fixed vegetation cover where only the land use change could alter it, but the vegetation cover couldn't respond to the climate change. It couldn't spread or decrease in forest extent. So those models are ESA-Earth 3 VEC, GFDL, the MPI ESM, that's the model that we are using in-house, and the UK ESM. And yeah, we use two pathways that hopefully the world won't see, SSP 3.7.0 and SSP 5.8.5, but to see what the effect of big climate changes could be. You see the CO2 concentration, how it evolves. Again, we are probably going to an overshoot and then down. In reality, both these pathways would go up in terms of emissions and CO2. The forest area, you see that in the SSP 5.8.5, it then flattens. There's no further deforestation, while in the SSP 3.7.0 there is. Keep in mind the SSP 5.8.5, it's really a lovely world, right? This fossil fuel-driven growth, it's rich, it doesn't have to clear the forest. The only problem is the climate change. And the approach then is we looked into the tree cover data to then infer from that on the forest cover loss. We did that from 1850 to 2100 and then also distinguished abrupt and gradual changes and then attributed those to land use change and climate change. That was done in the following way. So first, we identified the forest decline. It says here local forest decline because we did that for every grid cell of each Earth system model separately. These are just illustrative plots here. And then we distinguished also between forest decline that had a structural transition and one that didn't. So a structural transition would mean there was a forest, but afterwards there's a grassland there, or whatever, savanna. And a transition without a structural change means the forest declined, but it's still a forest. Then, when we had any such transition, we classified it into gradual or abrupt based on various statistical measures, played around there to find robust features, and then attributed it to the drivers of change. So we tried to exclude internal variability, weather variability, again by some statistical approaches, and then we're left with climate change or land use change. They were distinguished by using ancillary information. So the Earth system models also put out a variable that's showing the direct emissions to the atmosphere from a land use change. That's not the same as the land use emissions I've shown you earlier. It would not include legacy fluxes from the soil and so on. But it shows you that there has been an impact on the forest cover and CO2 has been released to the atmosphere. And we use that variable as this, so this is this FLUC threshold that's indicated here. And again, we checked that we found robust or meaningful thresholds across these 4 different models to say if it has been a land use change that likely triggered a change that we've previously detected, or if it has not been a land use change, and if it then hadn't been climate variability, it must have been climate change. So that's the idea behind it. Now, let's look into the results. So this is the first big chunk of it. This is looking into the forest decline. I'm showing you, apart from one slide, always the model mean, and you see the spread across models. It's big. What I'm telling you is robust across the models, but sometimes the spread is, in exact numbers, is quite big. But it's just out of, I don't want to hide anything, it's all in the paper draft. Just out of time, I keep with the means in general. So on the left-hand side, you see the SSP 370, and on the right-hand side, the SSP 58.5, and you see the result of the analysis already. The top is the forest decline driven by the land use change, and the bottom driven by climate change. So historically, the 2 scenarios are always the same. You see this line that distinguishes the historical period from the future scenario then. And when we look into the last few decades, we used 1950 to 2014, because we can then also compare to observational data like map biomass and others. We found that the forest area declines by 0.7 million square kilometers of the 5.5 that have been there. This is a bit less than what observational data shows you, but we also kind of understand why models are less sensitive than the observational data. In any case, this is about 20% of the 1950 forest cover that has been lost. You see the model range here, right? 0.7 million square kilometers, but it could be 0.2 or 1.2. It's massive differences across the 4 models. We used model ensemble. Members were available, but one model didn't have any. Now, 0.7 million square kilometers lost in the historical time period. Almost all of that was land use change. This is also what you see. The brown line goes down much steeper than the blue one. 0.6 million square kilometers is the deforestation, degradation, and only 0.1 is due to historical climate change. However, most of the forest losses that we've seen is structural transitions. It's really forest gone for good. There's a cropland there, there's a pasture there, there's maybe now a savanna state there. So the land use change, we realize, is really for expansion of agriculture. Now, if we go through the entire time series to the end of the century, we find that of the 1950 forest cover, 38% on model mean could be lost. And again, land use change is, or can be very important. So you see in SSP 37.0, the land use change till 2100 is about the same size as it has been historically. In the other scenario, we know it's flattening off because of the fossil fuel growth in the economy. However, the picture is inverse between those 2 scenarios when you look to climate change, not unexpectedly so. The climate change signal is smaller, but could still reach 0.5 million square kilometers lost in that extreme scenario. So SSP 370, that brings you to around 5 degrees change by the end of the century, and 8.5 to about 6 degrees, just to keep that in mind, because we're going to speak about degrees in a bit. Now, with 38% of the forest cover lost by the end of the century, we're crossing this magical threshold that Carlos Nobre had put out, saying that when 20 to 25% of the Amazon rainforest is lost, we're going to reach that tipping point. And so this is clearly something, if any of these scenarios comes true, then we'll see if this tipping point hypothesis is real or not. Now, this is the slide about the driver attribution. So the top smaller map is again the forest cover decline, but now you see it spatially explicitly. The little inset with the red area, that's the where we have structural change. And now you see also the difference between the scenarios. So what's different in the SSP 370 is that this western Amazon region is really threatened. There's more expansion there of agriculture in particular, while both scenarios still have this increase in these northeastern, in particular in the southeastern areas of the Amazon. So that's the pattern, and now let's look into the climate change versus land use change on these lower two maps. And there you see, so we grouped it. Low intensity means 0 to 25% forest decline has happened in that grid cell, and it was due to climate change or land use change. And this way you can more or less group it like that. So there's a white dot in the middle because we don't know, it's probably climate variability what's coming there, but in most regions we have a signal. Dotted means it's robust across all models, or the stippled pattern. So what we see is there's very high intensity from the land use change, and there's low intensity from the climate change, but it's more widespread. And the climate change also goes into these regions that are presumably still pristine and untouched by humans, really in the middle of the Amazon. And it's valuable for many other reasons than agriculture. There's many ecosystem protected regions in the middle of the Amazon. There's indigenous people living there. They will be affected by the climate change, while we already see the effects of the land use change in the surrounding areas. And the western Amazon, to look at that region a bit closer. So in one scenario, it would be affected by land use change. In the other, it's affected by climate change. No matter what happens, also that region will be affected by something and will show partly substantial forest cover decline. Now, so this is the slide with the 4 separate models. So you see the model spread here yourself. And this analysis aimed to identify the abrupt versus the gradual forest decline. What we did there was to impose a breakpoint analysis and then see and impose that on the climate change driven forest decline, and then see in which year there was an acceleration in the signal. And depending on the scenario, you found that the forest decline due to climate change accelerated in 2074 for the SSP 370 or 10 years earlier for the SSP 8.5 on average across the models. And it's robust across the models in a sense that all models showed at some point in the 21st century there's an acceleration of these climate change-induced changes. Applying that then, you can also look into the rates of change at the beginning of the century and the end, or compared to 1950 and the end, and then you see it's really a massive acceleration. So the forest area decline increases by a factor 7 or a factor 9 in those 2 scenarios. And then when you look specifically into the individual models and you take the one that's the most sensitive, then you see that this abrupt change occurs at a warming level of 2.3 degrees warming already. In other models, it's later, but this is since we don't know which model is better or worse, this is what could happen according to these models. And you all know that currently, when you believe the climate action tracker, we are set to, with the current implementations of policy measures, set on a path to 2.7 degrees. Maybe 2.1 if we are super optimistic. So this is about where this breakpoint could be reached already. And this, 5 minutes, perfect. Okay, thanks. And this is now when you compare the abrupt and the gradual changes in blue for the climate change, in brown for the land use change. Again, the model mean is shown here. The future forest area decline in general is more driven by land use change. This is what we've seen before, but the abrupt changes, those are driven by the climate change. This is what you see by this blue, dark blue widening towards the end of the century. These are decadal means that I'm showing here. All models are robust with respect to that statement. And then when you look into the spatial pattern of that, didn't show the map here, but the abrupt changes, again, are going to the intact forest areas in the central and the northern parts of Amazonia, and in SSP 8.5, also in the western part, where in 7.0 it's just cleared. Good, so the conclusion is if we continue deforestation and if we have unabated climate change, according to these 4 models that are the most comprehensive ones we have to date, around 38% of the 1950 forest cover could be lost by the end of the century. In this history, and also if we stay below about 2 degrees, it's the land use change that's the major influence on the forest cover. But if we go beyond that, then the climate change becomes more dominant, in particular also then for the abrupt changes. And so this could also mean that beyond 2100, there could be further destabilization implied if we don't reverse the climate trend. So that's the study based on CMIP6. And as I said, we try to disentangle climate change, land use change in plausible scenarios, which has a big value. But of course, then you need to work with the data you have. And we don't have this clean split up, right? It's statistically how we separate these 2 drivers. But what would be nice now, of course, is to have clean simulations with the same type of model to really separate those drivers. And then also try to understand at what warming level does what happen and what patterns of deforestation would lead to which change. Because here we had opportunistically these 2 scenarios, but the deforestation could also happen in quite a different way. And so this is where Lucas comes in. In ClimTIP, now in the Amazon work package, we do these simulations that are stylized, built on such simulations, and then they impose different patterns of the deforestation under specific, also lower warming levels. And then we will see if this precipitation recycling effect breaks down or not. So in that sense, ClimTIP is really a very nice follow-up to this CMIP6 based study. Thank you very much, and I'm happy to take any comments.
Good, thanks Julia for the nice talk. Questions? No? Okay, maybe first here.
Do you know the work of Jose Schankeman from Colombia, who's been trying to work on economic ideas for helping support the Amazon?
I don't.
Maybe it's not published yet. I mean, he's had an interest in this for quite a while. And there's a paper with Lars Peter Hansen from Chicago, who's a Nobel laureate in economics, and who brought their minds together on this problem. How to do it in a way that won't raise hell with the haves.
Okay, yeah, to see how to steer then the forest conservation. Yeah, that would be good. Again, it's not just a local problem, it's really something by global export that we have in our hands as well. Yeah.
Okay, sorry, there's a lot of questions, so be patient, people. The person in the back, I think, first.
Thank you very much. Thanks, Julia. One of the things that protects a lot of the models is actually CO2 fertilization from Amazon dieback. I wondered how you treated that. Was that separated out, or was that in your climate change impact?
That's in there, yeah. We separate out the land use change and the variability, and what's left is the climate change impact, including CO2. Right. But the dominant part in the future is the
Then I'm very surprised, because when we look at CMIP6 outputs directly, say in UKSM, we don't see any dieback really to speak of. It continues to accumulate carbon, and the forest cover is quite healthy. So there are models where that does happen, but I can't quite understand what you've done to get those outputs, because they don't look like the raw outputs from the models, to me at least.
It may be the selection of models, right? In the Paris study, you had 7 or 11 models. We have 4 here only.
No, I think we looked at less than that, but anyway, yeah. I mean, it is at odds with that, because we see a much larger range than you're suggesting. So 38% plus or minus a huge amount. And some models actually accumulate carbon rather than lose it, and accumulate forest actually as a result. So I think there is a bit of a disconnect here between this and previous studies, as far as I could tell.
I can check again, but remember these are also the high emission scenarios, right, where the pseudofertilization then saturates in many models, and then it's really the climate change impacts that hit it.
Okay, we have, I know that a few hands here. There's, we'll go for a question here online.
Yes, and this is from Pascal Bacanot. There are still lots of difficulties to represent this forest in climate models. What will be the major directions for comparisons and assessment of critical physical or biogeochemical aspects?
Yeah, thanks, Pascal, for that question. So we already see quite different behavior between GFDL and EC Earth on the one hand and MPI ESM and UK ESM on the other hand. And the first two models, they have age cohorts, so not necessarily full forest demography, but they have age cohorts and then they regrow in a different pace and so on. And you see quite distinct patterns between these two groups with more abrupt changes in the models that have these age cohorts represented, which we believe is an advantage in terms of model implementation. We also find that high-resolution simulations give different results, but this is not necessarily something on the side of the forest representation, but maybe more the land-atmosphere coupling and then the soil moisture feedbacks that come in there. And also the species composition, right? We have more and more evidence that a diverse forest is more resilient, and in particular, so a lot of the forest is already secondary forest in the Amazon, which has a different species composition. Possibly it reacts differently to the intact forest in the middle, yet in the models it's all the same PFT. So these are the paths I would take.
I think we have time for more 2 or 3 questions. Sorry, there was someone in the middle there. If you could please say your name and your affiliation.
Hi, I'm Arthur Argles. I'm from the Met Office, and I do work on vegetation dynamics with Jules' model. So one thing we've been doing recently is looking at how, say, mean NPP, for instance, or mean growth rate or mean turnover changes with like mortality rate, basically. So have you plotted sort of how turnover and land use, deforestation sort of have you looked at sort of a phase transition between forest and deforestation with that at all?
Are you speaking about carbon or about areas?
Areas, I guess.
Yeah.
So like, well, you could look at both maybe, but like just sort of looking at the phase plot of what are the key drivers of deforestation. Have you been able to look at that at all and see where that critical threshold might lie?
So we haven't done that, but in the ClimTIP work package, there's also, so Peter, you're looking into indicators, right, of different types of indicators for the abrupt transitions. So I guess that could be helpful in that work package. So maybe we can chat more about that.
Thank you.
Okay, we have one question online from Victor Brovkin from MPI.
Yeah, I actually can ask if you can hear me.
Yes, we can hear you. Please go on.
Yeah. So the question to Julie is whether these abrupt changes in forest areas are reflected in carbon storages.
So no, only partly. So this is coming back to Peter's question. The forest area and the carbon stocks are really not the same. And this is also what's driving me crazy. Whenever there's big fires in the Amazon, people then wonder why in the global carbon budget we don't have big emissions, but it's just not the same thing, right? Losing forest doesn't mean there's big emissions into the atmosphere. The timescales are just very different. And also the remaining forest does sequester more carbon, but there's also forest dying. And so these effects compensate each other quite a bit. But in that study, we wanted to keep it just with the forest area changes, also to be able to compare to observational data there. Yeah, but this would be a next step that would be helpful. But then there's other studies like the Paris study that looked into carbon.
Okay, I saw there was one hand there. Yes, please. We started a few minutes later, so since Julia ended up early, we are going back 2 or 3 more minutes over the time that was expected, but it's okay.
Yeah, so I think you almost touched on this. I think there's a recent study by Kathy Hohenegger at MPI that suggests if you run with convectively resolving atmosphere over the Amazon, you get a completely different let's call it vegetation climate feedback, local climate feedback, to what those resolution models do. So I'm just wondering what your comment is on that. I guess that would massively affect the climate change signal that you're looking at here.
Yeah, so they find a weakening in general.
I thought even a different sign, actually, but maybe weakening to a different sign.
Yeah, so the land-atmosphere coupling is much weaker, right? Yeah, we haven't brought those two scales together, and also the paper isn't overly conclusive on why this is so different, because we just spoke about in the coffee break, right? It's the same physics in the end compared to one of the models here, because the ICON and the MPI-ESM are based
I would say that no, they're totally different physics in the atmosphere. I mean, when they're running the ICON model, it's resolved convection, and it's
but the
radiation might be the land surface might be the same. Sorry,
yeah, and so somehow but it hasn't been explored, so I don't understand it, and I haven't spoken with Kati yet on why or what she expects on this different scale. It would be nice to have other high-resolution models there.
Okay, one final question. I saw one hand here. You still have a question?
It was the same question.
Okay, you.
Precipitation, regional precipitation is really important.
Yeah.
That was my question to you, because that's not in the CMIP 6.
Well, we do, so we do see precipitation goes down in those simulations, and they contribute to that forest decline. But then the question is, would it go down so much with a higher resolution? Yeah. So Lucas is also running a bit higher resolution, but not convection resolving. So to some extent, we're going to tackle it in ClimTIP.
Okay, then we have a final question here.
Yeah, thank you for your talk. So I was, you showed that climate change is driving forest decline, especially in the inner forest, in this what you call pristine areas. Do you have an idea of why it is that those areas are affected by climate change so strongly?
So partly it's that the land use masks the other areas, right? And the climate change signal is more spread, of course, with a lower intensity, and then it shows up there. And so you still have the more sensitive ecosystems. But no, otherwise we would rather have expected a pattern that moves in from the ocean towards there with the precipitation recycling hypothesis. No, I think it's simply that the whole forest is affected, and in the outer regions, the land use change dominates so strongly.
Okay, then we thank you, Julia, again.
Yeah, thank you very much.
And before the next talk, we have an announcement.
Thank you. So I would like to come back to you about the two outreach events. So there is one today. So today it is it will be 6:30 p.m. up to 8:30 p.m. So this one is in French. It will be held at ENS. So you are most welcome to gather. So the address is 45 rue d'Ulm, ENS. So if you might like to join, if you understand French, it can be very interesting. So tomorrow it will be 5:30 p.m. 6:30 p.m. So this one will be here with all of you. I hope so. So please stay tomorrow to this event that will be held in English. Thank you.
Okay, now we have 3 talks. The first one is from Lana Blaschke, who will join online. Lana is a PhD student at TUM and in Munich and PIC in Potsdam. She works with tropical forests and resilience. And I don't think I need to read the title. I think she'll talk about it. So yeah, go on, Lana. The floor is yours.
Hi, do you hear me properly? Okay,
yes.
Perfect. Hi, I'm very happy to be here today, unfortunately only online. So I'm going to present this work that I'm currently doing together with Sebastian and Marina and Niklas. It's titled Bridging Data and Theory for Monitoring Resilience Changes in Tropical Forests. So we will not only talk about tropical forests and resilience, but also about data. And as you can see in the background, we will mainly talk about satellite data, actually. So before we start, I would like to give a short overview of what we will talk about. We will start to talk about resilience in tropical forests. Actually, Julia already gave a very nice introduction, so we will keep that very short. But we will shortly see why there's empirical evidence and theoretical evidence why there could be stability, and look at the same study of Chris to see if it's changing. And then we will continue looking at ingredients and potential obstacles of resilience analysis, especially for tropical forests. And of course, there are always two ingredients, namely the resilience metrics and remote sensing products in our case. So yeah, we will look at those two. And then we will look about these vegetation products and compare them to what we expect from theory. And first, we will look at the noise in these products, and then we will look at empirical recovery wherever we can detect it. And then we will try to answer this question that everybody is interested in, like, is there actual resilience change in the tropics, and conclude with a short summary. So, okay, empirical evidence for biostability, we all probably know this. Marina Hirota published it in 2011, where they used a space for time replacement approach and plotted like mean annual precipitation against tree cover for the Amazon, but also for other tropical regions. And you can see that there's like a mean annual precipitation range where there's actually high tree cover state possible, but also low tree cover state. And so that's why we could assume that there might be a tipping happening once we cross like the mean annual precipitation threshold that we see here. That's the main empirical evidence that we have. The main theoretical evidence, Julia also already explained, like the rain is coming in from the Atlantic Ocean, it's transported by the trade winds, and it rains down, like here in the beginning of the Amazon, like the east. And then actually the moisture is taken up by the trees, and they evapotranspirate it back into the air, and then the moisture is transported even further to the west. And that's how the Amazon basin produces enough rainfall to maintain a rainforest in the entire basin. So that's why it's interesting to look at resilience in the Amazon or in tropics in general. And Julia also already mentioned this study by Chris and his colleagues that was published like 2.5 years ago, I think, where they could find like a lot of increase in autocorrelation, which is a measure of resilience change. And so it is possible that like the Amazon rainforest is losing a lot of resilience. But we really want to get robust results. So we should think about like the ingredients that we're actually using for these studies and the potential obstacles that those ingredients can put. So as I said, the first thing that we always use are resilience metrics. And as you might all know, the most common ones are autocorrelation and variance. So what we are usually assuming is that like there's a tipping ahead in our time series that we are like analyzing, and at some point it will tip. Then we usually see like an increase in autocorrelation as well as variance before the tipping is happening. And now in this case, this is an artificial or synthetic time series with white noise. But what was already known, but Andreas and Niklas showed in the study as well, is that like if you have, for example, autocorrelated noise without any tipping, you can also get like an increase in variance and autocorrelation without any tipping being had. So that's the first thing we will look at. Like noise can actually influence our resilience metrics, so we should know about our noise in our data. And talking about data, that's always the second thing that we also use for our resilience studies. As I said, in our case, it's remote sensing vegetation products. And probably the most well-known or most used one is the Normalized Difference Vegetation Index, short NDVI. And the study by Taylor and Niklas, they actually looked at this NDVI, calculated trends of lambda calculated from autocorrelation as well from variance, and then looked if this is consistent. And now they found some very interesting thing, namely that basically all the tropical forests, they have either inconsistent or undefined lambdas. So we could conclude from that that either the comparison is problematic of those two, or that NDVI is actually problematic for tropical rainforests. So yeah, we should be careful about the data that we're choosing. There's also another reason why we should be careful, because also Taylor, but with a lot of other colleagues, they showed that for merged vegetation products, we need to be careful. Merged simply means that like we have a lot of sensors collecting data, but we would like to have like a time series as long as possible. So that's obvious idea to just merge it into one that covers the whole time span. And as you can already see here, these are like different sensors. It's actually synthetic, but like it represents different sensors. You can see that they all have different signal to noise ratios, and also that like for different time periods, different amount of sensors actually collect the data. So if you merge this now, of course, depending on how you merge it, but you can in general, it's likely that you have some influence from like the signal to noise ratios and the amount of sensors that you're using. So this blue one here is like the final product that you could get from it. So, and you see it's influencing the variance and the autocorrelation of the product. So you should be very careful about using autocorrelation variance for merged data. Not in general, but as resilience metrics, of course. Yeah, so the goal of this study now is to find out which combination of remotely sensed vegetation products and resilience metrics are suitable for resilience analysis in tropical forests. And yeah, as these are actually the regions that we will look at, so it's only intact forest. We try to exclude human land use here, yeah, because we want to understand the resilience change in the natural forest or original forest. And we will compare like a lot of different vegetation products from different sensors. So that's just an example so that you can see like merged average time series of like 16 different vegetation products that we will look at. And now, as we said, the first important thing that can influence our resilience metrics is actually the noise of our data. So the idea here was simply to estimate the noise and check its properties. So we simply do this for each grid cell that we have a time series, and for each of these time series, or we have like one time series per vegetation product, we do like some kind of regression, and then with this regression, we get a time series of the noise, and we can analyze the statistics of those time series. Now, the first thing that we are interested in is actually if the noise is white, so if it's not autocorrelated. And so we use the Broich-Godfrey test on those time series that, like the noise time series that I showed before. And we plot here its p-value. And if the p-value is very low, then we can be pretty sure that like the noise is not white. So it's probably autocorrelated. And yeah, these are the results for all of our data sets. And I guess we can conclude from that it's very unlikely that our noise is white for any of the data sets. So we should be careful here. This especially is influencing or could influence the autocorrelation as a resilience matrix. The other thing that we are interested in, or that could like be a problem, is like if the noise amplitude is actually changing over time. This would have a quick influence on the variance. So here we did the same. We estimated noise time series on like sliding windows, and then calculated its amplitude and then the candle tau value of those amplitude time series. And now if this is close to 0, then actually the amplitude is pretty stable or constant. And if it's like 1 or -1, it's the increasing or decreasing respectively. And these are the results. So what I find very interesting here is that like especially the merge data, which are all those that are hatched, so these 7 here, especially for those, you can see that like a constant noise amplitude is pretty unlikely. But to be very honest, also in the other data sets, we do have a lot of cells where the noise amplitude seems to be changing. So also constant noise is not very likely in our data probably, and we should in general be careful about autocorrelation variance when applying them as resilience metrics. That's the noise. So now the question is, how can we actually ensure that the theoretical resilience metrics like autocorrelation variance measure recovery? And this is also nothing new. We came up with the idea of following Taylor's paper and estimate a direct lambda empirical, like the direct empirical recovery rate, wherever we can detect a perturbation. We apply this to all the time series we have, and then we fit like an exponential function. From this, we get like a lambda, which is our recovery rate, and we get like a measure of goodness of fit of this, fit, how well the pink fits the other time series. And then for this, we get like maps for different locations wherever we can detect such perturbations. We get like a lambda empirical, and then we have also our maps of, for example, autocorrelation or variance. And the idea now is simply to check the correlation of these theoretical resilience measures with the empirical ones. And the first question that we will try to answer with this is like, which theoretical resilience metrics measure recovery best? And to do so, we will take averages across all our vegetation products that we use. So what you will see in this plot is actually on the y-axis, the average Pearson correlation, average because it's averaged across all vegetation products, as I said. And on the x-axis, we have like the goodness of fit of the actual empirical recovery rate. So the higher, the better the empirical, the pink line fitted the other one. And the colors now will be the different resilience metrics that we are using. We will look at lambda GLSAR. This is like a regression that takes correlated noise into account, and then a corrected variance and autocorrelation. And these are the results. So what you can see here is that lambda GLSAR and autocorrelation actually perform best, and that the corrected variance, even though it's corrected for the noise amplitude, performs a bit less good. So these are the results comparing the resilience metrics. Now, the other question is that we can ask is like, in which data sets can these theoretical resilience metrics actually measure recovery best? And now we will just have like exactly the same results, just that it's not averaged across vegetation products. So yeah, here now you see again, like on the y-axis, the correlation coefficient, and on the x-axis, all the different products that we are using. And you can see now, like, this is only for the lambda GLSAR, but of course we would have the results for the other ones as well. It's just too much to show. So, and what you can see here now is that the best data sets that we might find, or in which it is most possible to actually estimate recovery with those theoretical metrics, is NDVI here. Actually, this other one is almost the same, so we only will use NDVI. And these four here in the end, like CVOD from AMSE, and C1, C2 VOD from AMSE2, and the LVOD from ESMOS. So now we can actually try to answer the question, like, does resilience change in the tropics? So we will use exactly this one indicator, the lambda GLSAR, and those 5 data sets that we have used, that we found to be the best. And we look at spatial averages here now for the 3 tropical regions. And these are the results. So this is the Amazon rainforest, the African and the Asian. And the different colors are the different vegetation products. And so what I found very interesting is that they actually agree very much in the general trends or the general behavior of this lambda GLSAR, even though they are really from completely different sensors, wavelengths, whatever. So yeah, this is the first conclusion from this. And the second one is, I guess one can see some resilience loss, especially pronounced until the year 2018. And then we don't really know how it goes until now, because we can't exclude human land use changes in the last 2 years. So that's the results. And we will now conclude with a short summary, we started with the ingredients and the potential obstacles and saw that like noise can bias the resilience metrics and data can be problematic. So the first idea was to investigate the noise. And we found that it's not really what we would hope for from a theoretical perspective of resilience analysis. And next we checked if the theoretical metrics actually measure recovery. And we could find that lambda GLSAR and AC1 perform best, at least in our case. And also in our case, the 5 best data sets were these 5. So then when we looked at an average lambda GLSAR across time, we could find that like for these completely different vegetation products, actually they pretty well agreed on resilience changes. So what we would conclude from this is like if you get the right combination of data and resilience metrics, then you can actually do resilience analysis for tropical rainforests that are robust. And yeah, there was resilience decrease most pronounced until the year 2018. So that's it. Thank you very much. I'm happy to take any questions like that.
Thank you. Yeah, thank you, Lana. So we will collect questions for at the end of the session. And I'm happy to introduce our next speaker, who's Sandra Zimmermann. She's a PhD student at PIC in Germany. And Sandra, completely different topic. She works on climate change impacts on humans. At PIC, she's also our expert on the Kama flood model. And she's contributing to TipESM in the work package 6 on tipping and social systems. So the floor is yours, Sandra.
Thanks so much. Oh, it vibrates. Maybe because many of you work on ice sheet modeling and this is pretty far away from your research. Let's start with a definition of internal displacement. And internal displacement is a forced form of human mobility. So it's involuntary and it also takes place within the borders of a country. And we usually differentiate between 2 forms of displacement. There's violence and conflict and disaster-induced displacement. And I think interestingly, as opposed to the perception of many, more people are being displaced due to natural hazards on an annual basis than there are to violence and conflict. And what you should also see when looking at the different colors is that as opposed to displacement due to violence and conflict, disaster-induced displacement is a real global phenomenon, which does not just take place in very vulnerable countries in the global south, but overall. So countries including Canada, New Zealand, and Australia have reported their highest numbers in internal displacements due to natural hazards in 2023 globally. So ever since recording started, which is only a period of 15 years, more than 400 million people have been displaced due to natural hazards globally. We also know from these records that the vast majority of these displacements occurred due to weather-related extreme events as opposed to geophysical extreme events, including, for example, earthquakes. What we know is that with increasing global mean temperatures, the frequency and intensity of these hazards will increase too. This is the example for floods, or riverine floods to be precise. So it's not really surprising that the idea and the topic of disaster-induced displacement has gained increasingly attention in international climate negotiations. There is a special task force on forced displacement under the UNFCCC, and the COP27 cover decision has even recognized disaster-induced displacement as one of the severe adverse non-economic losses from climate change. So if the frequency of these hazards that trigger displacement, as well as the intensity, will increase, most likely people will be displaced more frequently, but also with the increasing intensity, the damages to homes as well to existing infrastructure in the community. But what we know from disaster-induced displacement research is that people are being displaced as long as their homes are not reconstructed, as well as basic services, including electricity and water and sewage, is not being served to them. So if more damage is being done, then the reconstruction time also increases, and along with it, most likely the duration of displacement. So looking at that, the main question we are trying to answer within this project is, will at some point IDPs, short-term for internally displaced persons, decide not to go back home? And then we're looking sort of at the concept of habitability, which is a pretty hot topic in the human mobility climate change nexus research. So in order to answer this question, we need to be able to project disaster-induced displacement risk into the future. Luckily, there have been studies which do so, one for China and one for the entire globe. This is only on flood-induced displacement. And our research currently also focuses on flood-induced displacement, for one, because it's a fast onset event, and as opposed to slow onset events, including drought, there's a direct causal link. So the flood happens, people are being displaced, and you can directly relate the cause and the displacement. And also, as opposed to, for example, tropical cyclones, it's a lot easier to model, because tropical cyclones, there's the fluvial floods, the storm surge, and the wind coming together. And floods trigger the highest proportion of disaster-induced displacement, so there's also that reason for it. But what you can see from this global study is that both climate as well as population change will increase displacement risk in the future. Both studies that do that use the same methodology, and what we realized is that actually they have not been validated, so we don't even know if they correctly capture displacement. This is true for all displacement models that currently exist. So the first step that we've done is basically gathered all existing flood-induced displacement models and compared how they model displacement, and also evaluated them against existing displacement records. And what you should see here is that the two models that sort of use the methodology, which can be easily used for projections, actually heavily overestimate displacement risk. So this is not necessarily a problem if you do relative changes, but it is if you're looking at absolute displacement risk. So the first step is basically to go back and build a new displacement risk model before we perform projections, and then examine potential tipping in disaster-induced displacement risk. And as any other flood-induced displacement risk models, our model grounds on the concept of risk, so meaning risk is always a combination of the hazard, the exposure, and the vulnerability. We also decided to divide our risk into two components, one being the occurrence of flood-induced displacement, because not necessarily, and ideally, and this is also the case, not every single flood triggers displacement, but we simulate floods on an annual basis and for the entire globe. And the second is then, if displacement takes place, how many people are being displaced out of the community, so the magnitude of the event. Our hazard is retrieved from like a flood modeling chain, which starts from the EasyMIP framework, because I'm part of the EasyMIP community at PIC, and we use EasyMIP 3A data from global hydrological models, and their discharge feeds into, as Stephanie already mentioned, a hydrodynamic model, which is also a process-based model, which basically takes the discharge and redistributes it along an existing river network, and then provides us with specific characteristics on our hazard, including how long the flood lasts, with which velocity the water flows, the return interval, so how rare and extreme an event is in comparison to its historical period, as well as the flood depth, and along with it, the inundated area, which we use in combination with gridded population data and intersected with the inundated area to determine basically the people that are affected by a flood event, which we assume to be the maximum potential impact, so the maximum number of people that could possibly be displaced by that simulated flood event. We also account for the vulnerability of the community, following a sort of top-down approach to vulnerability, including socioeconomic and political indicators. We include the population density because risk research has shown there's a vast difference in the vulnerabilities of rural and urban communities. We also include information on existing flood protection levels, which basically is supposedly to account for flood experience as well as preparedness and the adaptation of a community. Then also the critical infrastructure index, which is an index which combines information on existing electricity and water and sewage infrastructure, but also health infrastructure and electricity. I think I mentioned that already, but anyways, electricity infrastructure. So this is sort of an indicator which gives us an information how economically thriving a region is. And then finally, the infant mortality rate as an indicator for extreme inequality, showing if there exists most vulnerable groups and if a community is capable of providing the most basic and important services to its members. So all of this feeds in a two-step model. Both are Bayesian regression models, the first one being logistic, so does displacement occur or not, and the second then, how many people are being displaced. And we use this setup to, for the first time, try to disentangle what roles exposure, hazard, and vulnerability play in displacement risk, both in the occurrence as well as the magnitude. And we run different model runs, the most basic being the exposure-only model. So we do have the exposed population related to the number of displaced people or whether displacement takes place or not. And then adding the hazard indicators, the vulnerability indicators, and both. And what we find here when evaluating the model with the widely applicable information criterion, so the lower the value, the better the model performs. It also, well, it sort of evaluates the performance by also accounting for overfitting, so the complexity of the model. And what you can see here is that the green bar, which includes the vulnerability indicators, as opposed to the purple bar, improves the model a lot more. So when it comes to the occurrence of displacement, the vulnerability of a community is decisive. When we look at the magnitude, however, this picture changes. And in fact, we see that the hazard indicators, so how deep the water is and with which velocity it flows and how well extreme the event is, decides on how many people are being displaced, which is an exciting result because we see that you sort of less vulnerable communities are less likely to see displacement, but when, for example, flood protection measures fail, it's the hazard that decides how many people are being displaced. I'm sort of wrapping up this project, or will be for a couple of months, but we also used this to assess the predictive power of model to perform projections within this project for both the occurrence as well as the magnitude. And brownish colors show underestimation, greenish colors show overestimation, and we'll see that our model both over and underestimates. Interestingly, for example, we overestimate occurrence in the Americas but underestimate their magnitude. We also see that heavily populated countries, including China, India, and Pakistan, the magnitude is overestimated, but mainly because the exposure is pretty high, and exposure is the most important predictive variable in our model. Nonetheless, if we consider the uncertainties along the entire displacement risk modeling chain, as well as the uncertainties we have in reported data due to errors and biases and gaps, this is a pretty feasible setup to perform projections and a lot better than many other setups we currently have. So we've done the first step. And then the second step is to perform projections. And we're basically going to use the same setup. And instead of using EasyMIP3A data, it's going to be EasyMIP3B data for different RCP SSP scenarios. We're also going to use population projections. And we're still figuring out vulnerability indicators for which gridded projections exist, but this is then going to provide us with spatially explicit information on communities on a province level on a yearly basis, whether they're most likely to experience displacement or not, which then gives us the possibility to look at the return intervals. So when does displacement take in the communities? How do these recurrence intervals change over time? Do they become more often, less often? Does displacement occur very frequently or very rarely in these communities? And this is basically the first important step to assessing our definition of tipping and displacement. And the second step is then to determine the duration of the displacement. Based on the assumption, as I already said, if your home does not exist, you will not return back with your entire family. So basically we ground our assumption is basically that as long as your home is not reconstructed, you're being displaced, and once it's reconstructed, you will return. So the reconstruction time of the home is equal to the duration of the displacement. And we can construct the duration or the reconstruction time by first assessing the damage to a building, which can be done with building damage curves. There's both empirically derived as well as model-derived curves, which use different building types and then relate the flood depth, so one of the hazard components, to the percentage of building damage. And depending on that percentage of building damage, we can then assess the reconstruction time. This is a stepwise function, empirically derived, but it basically provides us with information on how long it takes for a home to be reconstructed. And basically, our main assumption is that if the reconstruction time at some point exceeds the recurrence interval, so the time at which displacement will take, occur in the first place, then displacement will become permanent and we'll actually see a tipping in the permanence of displacement. And with that, I'm already at an end because it's already really late.
Thank you so much, Sandra, for a really great talk. And then our last speaker for today is Friederike Frø from the University of Bern in wonderful Norway. And she's contributing with her NOR-ESM simulations to a whole lot of work packages in TipESM, but also the work package 6. And now we move into the marine systems. And we hear a lot about, I think, carbon cycle and biogeochemical processes, maybe. Thank you, Rike.
Thanks, Steffi. Yeah, I hope you're still awake for the last talk. So I'm going to present some work we have been doing on the response to net zero and negative emissions in the deep sea and at the seafloor. And we are using these idealized experiments with NOR-ESM that are not so different to the TipMIP experiments that we have been running. We essentially have oh yeah, that's not really, okay, I'm not doing that. We have a ramp up to different cumulative carbon emission levels over 100 years, followed by zero emission over around 300 years. And then we have 6 different overshoot scenarios. This is the lower figure that shows that we have an overshoot starting at the peak of emission towards 1,500 petacam of carbon cumulative emissions, as well as some delayed overshoots after 100 years to assess whether or not there is an impact of delaying mitigation in time. The response in temperature is quite interesting. So we have the warming following the ramp up, but then at the zero emission runs, we don't have a linear or like a constant temperature response. That is because we have this strong response to the AMOC. So the AMOC declines and it recovers, and that's followed by the temperature. And we see the same actually as well in these overshoots. However, they are after the AMOC recovers, we have kind of an overshoot. So the AMOC recovers more and then goes down again. Anyways, in these simulations on a global scale, we don't really find an indication of tipping, and we don't really see that there is a different trajectory after the overshoot. However, we were also interested in the regional and local response. So how sensitive is the deep sea, what happened below 1,000 meter depth in the Atlantic, especially for different habitat stressors? Is there sensitivity to the emission pathway, and are these signals reversible or not? When it comes to reversibility, so I don't really have to explain it so much to this community here in the room, but essentially what we want to know is from a present-day climate point in a ramp-up to our peak emission, if the trajectory is the same on the ramp down as well, then we would have zero hysteresis. So this would be the straight line. This would be the straight line over here. If we had no hysteresis, and if we have strong hysteresis, then this area below this curve is extremely high, or is like larger. And our system would show reversibility if we end up at the same point in time at present day on the ramp down, and we have irreversibility if this loop remains open. In our simulations, we can apply this framework and start our present day sort of point, that's T1 here, at the point in time where we reach our emission, in this case, the 1,500 petrogram carbon, and we ramp up to a peak emission, and then we have this point here where we have the end of the overshoot, and then we just run net zero emissions for the last 200 years. And in temperature space, that would look like this in the Atlantic. So we continue to warm in the deep ocean, and then we reach peak emission, and we have this overshoot, but it continues to warm at the end of the overshoot. And if we just keep running, there is some sign of reversibility, but in the time horizon of the simulation, we don't reach this point again that we had for the present day. Anyway, when we look into now some results for temperature, this is here mean temperature between 1,000 and 1,000 meter depth in the Atlantic going from north to south. We have considerable warming that is weakest in the north and that is stronger in the southern boxes. And we have quite some variability that is responding to circulation changes in the northern Atlantic and in the subtropical parts, and it's a bit more smooth in the South Atlantic. And we can now calculate this hysteresis area, which is really high. So this north-south warming gradient that actually results in this really strong hysteresis pattern that is more dominant in the southern part than in the north. And this is really why this is really because the deep ocean that just continues to warm after the overshoot and has is irreversible by the end of the simulation. And if we quantify this, so the stippling actually shows what is irreversible after 400 years, then we can say that roughly 70% of the Atlantic has not returned to this defined begin of the simulation or present day point. This is really interesting. We can also look at this over different, over the entire water column for the other overshoot scenarios. So these are the different lines here showing all the other simulations. And essentially, we see stronger hysteresis during these delayed overshoots, and of course also stronger hysteresis that is not reversible by the end of this simulation in the higher emission pathways. And the signal is way more pronounced here in the South Atlantic than it is in the northern part. All right, now we can do the same exercise for oxygen, for example. That is another habitat stressor that we are quite interested in. And again, we have much higher variability in the north than we have going further south. But interestingly, in the subpolar North Atlantic and in the subtropical regions, we see this continued deoxygenation. However, if we go into the South Atlantic, at this depth level, we have an increase in oxygen. And this increase in oxygen, that is not new. If you can, and that's not a new result. We know that in this intermediate depth levels, oxygen increases due to the weakened stratification, and there is less vertical transport, so less of the deeper and older water masses mix up. And in fact, below somewhat 2,500 meter depth, we see this deoxygenation signal in the South Atlantic as well. Yeah, and that's just to show the oxygen saturation, which is a response to the temperature, to the warming. So that's consistently declining over all these boxes as well. So I'm not going into detail here. When we look at the hysteresis area, then we find a similar pattern. So we have this continued and weak deoxygenation in the North Atlantic that results in this weak hysteresis and this stronger ventilation at mid-depth in the southern Atlantic. That leads to a stronger hysteresis despite this warming-driven loss in oxygen saturation. And overall, we have around 40% of the Atlantic that shows these irreversible changes. And again, this is the same figure as before. during the delayed overshoots, we see stronger hysteresis as well as during higher emission pathways. And the last driver that is important is the calcium carbonate saturation state. This is particularly important for calcifying organisms that rely on a saturated or an oversaturation in terms of this calcium carbonate for building their shells, for example. And we have, depending on the starting point, we see over time this loss in saturation state. Actually, in the northern parts, this area, we find that by the end of the simulation, the entire, or in all simulations, we have undersaturation reached in this depth level with only some recovery. The same applies in the subpolar North Atlantic, and well, further south, it's quite interesting because we just continue to lose this carbonate over time. And then again, we can look at the hysteresis, and yeah, approximately 65% at this depth show this irreversible change in calcium carbonate saturation state. Okay. And the same again, I'm sorry. The message stays the same, but it's interesting to look into these different simulation runs, just to say that this is really an argument for not delaying mitigation, because we always find stronger hysteresis during the delayed overshoots and in the higher emission pathways. Now, why does it matter? We know that the warm water corals, for example, are considered as a tipping element. So we're more interested in the cold water corals. So these are these reef-building corals that we find in the entire North Atlantic, but more so in the northern parts. And then again, they are located at the seafloor, and they are quite interesting animals. They actually may benefit from higher temperatures. However, their metabolic costs increase the higher the temperature gets. And when it comes to aragonite undersaturation, then it may not affect the living specimens, but for the dead reefs, this is important, because you might degrade these coral reefs, or they just start to dissolve in case of undersaturation. But again, these metabolic stimulation by higher temperatures that may actually partially offset this negative effect by acidification on the growth of the corals, but that just requires more energetic costs. So what does it mean? You just need to supply food. If you have more primary productivity at the surface, more material sinks to the seafloor, and the corals can eat that to maintain these, to maintain their growth. And in terms of oxygen, that's actually not really a limiting factor for the cold water corals. They are already in these deeply hypoxic or close to hypoxic domains. But again, their capability to adaptation to this may be facilitated by surface ocean productivity. So I think I'm going quickly through this just to show you what happens at the seafloor in these simulations. We have a strong warming, also with some strong hysteresis. We do lose oxygen. I'm just showing this for consistency. And again, it's irreversible. And we have this loss in calcium carbonate saturation, and we have in the deeper parts at the seafloor, undersaturation reached. That's yeah, quite stressing. So what I then did, and I'm just finishing with that, I made a very crude subsampling of the model to where I actually find the corals, and I just construct this habitat index where I define that the habitat is sustained if the warming is less than 2 degrees Kelvin, if the calcium carbonate saturation state is above 1, and if I find a positive trend in export production at the sea floor, at 1,000-meter depth. And what we then see in the North Atlantic over time is that this fraction of potential habitat declines quite dramatically and reaches values that are very low in the subpolar North Atlantic, and only recovers to a certain extent, so only 20 to 40%, or at least 20 to 40% of this fraction of potential habitat, or that is lost over time. Okay, I feel like I'm talking a lot. Well, these are the conclusions. So essentially, we find the strong irreversible warming. We have this reventilation pattern in the South and tropical Atlantic, and I didn't mention this, but this may actually be beneficial for some benthic species. So there are definitely winners and losers when we talk about marine potential habitats for fish. And we can combine the saturation state of aragonite, the warming levels, and this measure for food supply in order to constrain this potential habitat. And with that, I'm done. Thank you for listening.
Thank you, Rike, very much for a really great talk. And now we have about 10 to 15 minutes left for questions. I know it's really late, but I want to encourage all of you to ask questions, especially the younger researchers. Don't feel shy. Please raise your hand if you have any questions to any of the three speakers. So we had Lana on Amazon, Sandra on human displacement, and then Rike on marine systems.
Hi, I'm Arthur, again from the Met Office. So Lana, I've got a question on your approach to modeling resilience, estimating resilience in the Amazon. So you highlighted in your introduction that autocorrelation and variance can be used to predict tipping points, but it isn't necessarily, like, it can sometimes not predict tipping points. So is your Lambda term from your exponential recovery, can that be used as a predictor of tipping points?
I'm not sure I understood the last part of it. So
how
autocorrelation and variance is what?
Can you hear me now? Is that a bit better? How can you use your Lambda resilience term to predict tipping points?
So the Lambda empirical, you mean?
Yes.
Yeah, so the problem is you only get so the question, if I understand it right, is like, can I use this one directly to look like on what's going on in my tipping elements? Is that right?
Yes.
Yeah, the problem is you like need a perturbation for it and then the time series afterwards to fit your like exponential function to it. And so you usually have only one perturbation per time series. You can't get like, you can't detect any changes in this Lambda empirical because you only have one value.
Okay.
Maximum.
Does the perturbation correspond to, what does a perturbation actually mean? Like, in terms of the forest? Like it's a big drop in the NVDI, but is it a permanent loss of forest or not really?
Okay, sorry, the audio quality is not so good. So the question was what the recovery actually means in the data set?
Yeah.
Yeah. I mean, yeah, that's actually a very good and very interesting question because this depends a lot on what these data sets actually measure, and this depends on like what sensor you're using and so on. So especially for the NDVI, which is like more in the visual optical wavelength spectrum, like recovery could also just be a regreening after, like, you know, a tree died and then there comes some grass afterwards. And potentially NDVI cannot really detect this. So yeah, like from this perspective, the microwave-based data sets might actually be much better.
Okay, thank you.
Okay, thank you. Other questions? Thomas?
Thomas Fröhlicher, Uni Bern. Thanks, Rike, for the nice talk. Do you think this potential habitat metric, could that be used for our adaptive scenario and actually to develop safe mitigation pathways? And related to that, how good is actually your model in simulating these low oxygen zones and the other stressors?
I think we could definitely construct a niche predictor with having multiple thresholds or multiple species sort of related warming thresholds or oxygen needs. I think the problem always is that they are species specific, and one needs to maybe find a way to combine multiple of these metrics in one. So I'm also working with this metabolic index, and we are trying now to construct something that is a bit more including more species, but just one. But it's very difficult. But yeah, we could definitely use it. And for your second question, modeling these low oxygen regimes, I think that's a problem for all Earth system models. I think especially for the deep ocean, we are not quite certain how well we do. For example, I think in NORISM or in Hammock, we have an infinite oxygen supply in the sediment. I'm not sure how realistic that is, but that's just a feature that a lot of ESMs have. So we definitely should not over-interpret.
Thank you, Andrew.
Thank you. I've got a question for Sandra, actually. I guess I'll pass. Oh, you got the microphone still. That's good. So I was really interested in your approach for risk modelling, and particularly around the vulnerability data sets that you chose. So I suppose I've got quite a lot of questions around that, but I'll try and condense it into one good one. So how do you kind of calibrate your risk model against observations? Because it's really difficult to get global observations of these kind of measures of displacement, for example. And then how do you choose your vulnerability data sets? And then I guess the follow-up question is, what are how can you identify thresholds in these models that you produce that we can confidently say that that's sort of a tipping in that system?
That's multiple questions. I'm trying
Sorry.
to get them over. No worries. So we do have global data. I think, I'm not sure, but I can also use.
Does a microphone work for people online? Okay, cool.
So there's a global data set from within the period of 2008 to 2023 by the Internal Displacement Monitoring Center, which provides information on at least the country level. And then I use a geolocation algorithm that we developed. So basically we're using parts of the data set where we're able to draw like the location names from the event name and geolocate it to a province or at least district level. So that's currently what we're working at. So it's not grid level, because this is basically, there's research that basically divides then displacement numbers into different districts, but this I think is more uncertainty than aggregating it to a bigger level. So we're currently looking at province level. We also looked at district level, but that excludes a lot of displacement events, so we end up with a much lower number. So it's currently, basically weighing this. The vulnerability indicators are sort of based on what we already know from displacement vulnerability. So like a previous Binek, Mester et al. Has done a study on the vulnerability of flood-induced displacement, and some of the indicators are basically drawn from that, but also from the overall risk research. Also, I fought a fight against including the GDP because I don't want to enforce the narrative of we can grow out of this, although I'm pretty sure, I've never tried it, I'm pretty sure it would work pretty well. But actually I also included, for example, the number of internally displaced persons that exist because they're particularly vulnerable, and our evaluation study showed that having lots of displaced people which live in crowded camps, and then there's another extreme event happening like floods, they sometimes make up to a fourth of the people that get redisplaced. So I guess it grounds on risk research, and then my personal beliefs. And then thresholds. Yeah, I guess, we're still working on that. So I guess when we see the first model runs, we're trying to figure that out. But we have, a colleague of mine, Karim Santoud, has looked at the recovery periods of floods already, and has seen that, from extreme flood events that trigger displacement the most, we see a massive decrease with global mean temperatures increases. So that's the first step. But I hope I'll be able to answer that in a year from now, the latest, or end of this year.
Great, when we deliver our first milestone, so that sounds
exactly
great, Sandra. Okay, we have time
Obviously
for final questions, maybe two, but yeah, go ahead, please.
So I'm Jem from the DMI. I have also a question for Sandra, more detailed one. And how do you calculate this, let's say, duration of a flooding event, for example, hazard? So I can imagine, because I'm also calculating quite often, I can imagine you can, simplest way probably you just calculate the time over a threshold. But this kind of duration, normally in the initial phase of a hazard, that's okay. But especially in the retreat phase of a hazard, because retreat phase of hazards, like flooding events, that's often stepwise and very slow down processes. That's why I see your map, if understood well, that's you often kind of underestimate the magnitude of the displacement. Could that be the reason for that? Thank you.
Okay. So we basically define the duration of the we count the days that the discharge exceeds the 2-year return interval, and we fit extreme event distribution to the annual discharge. So this is part of also the return interval. It's not given by the model, but I didn't have time to explain that. And we decided, so basically on Vilna et al. 2018, I'm not sure if you know that, but they define basically the natural protection of a riverbed to be a 2-year return interval, because that's also how KMA flood works. It has a basic, right, it used that rectangular shape, and it basically used the annual mean discharge, so every single year it exceeds and there's a flood occurring. So we basically count the days before and after that, but the flood duration is also not the indicator that works the best. It's actually the return interval, and I'm also still working on the validation, but we also use different flood protection levels because we overestimate flood a lot if we don't apply flood protection levels then. But then when we use flow-post flood protection levels, we underestimate it a lot. But surprisingly, we don't see massive differences between the flood protection levels, although the exposure numbers also change drastically along with it. So I'm not sure if we underestimate the flood, that this necessarily contributes to it. I think there's lots of other uncertainties in that chain that contribute a lot more. Generally, we're looking at massive uncertainties. But yeah, does that answer the question?
Okay, great. Thank you so much for your questions. And let's have another big round of applause to all our speakers. And Shuting will close today.
Thank you very much. I think it was very interesting presentations. Just a reminder, the outreach event today, you see the address, and it's in France. So everyone are welcome, as we have here from Fredrik. Otherwise, I would like to thank everybody for today, and particularly the presenters.